Marita, can you please check your email?
Yes, I have it. Thank you.
Okay, we can start.
I can start. Hi, everyone. I am Marita Lira. Today, I'm going to be the chair of this last session of Doc Fun Talks. I am really glad to be here. I hope you are enjoying all this week. I ask you to hold the questions to the end of each talk. You can use the raise hands in the Zoom. Who is in the Zoom, please use the raise hands. And who is in the seminary room, I ask for the people who is there to help me because I cannot see who is raising the hands. So let's start the talk. Today, we are going to start with Raphaelle Houdeville, and she was born in France. She has chemical engineer degree for the university, for the École Supérieure de Chimie Organique et Minérale, ESCOM, in Copenhagen, France. And she is nowadays at ALBA under the supervision of Dr. François Faute, and at ICMAB under the supervision of the Professor Rosa Palacin. Her title of the project is the synchrotron powder diffraction on operando batteries at no ambient temperature conditions. Raphaelle, whenever you want, I leave you the floor.
Okay, thank you, Marita, for the nice introduction. So today is my pleasure to start with the presentation. My talk will be about the co-intercalation mechanism of propylene carbonate in titanium disulfide. So I know it's a bit, everyone is a bit lost with this title, so I will start to introduce my topic, and then I will present two types of system in which I studied co-intercalation. So the first lithium system where I made most of the observation, and then I try to transfer all the knowledge we have acquired with lithium to calcium systems. So then I will compare a bit both systems and conclude. So to start with the topic, I wanted to introduce a bit a very quick history of titanium disulfide as a cathode material. So in the 70s, Stanley Whittingham identified titanium disulfide as a possible cathode material and tried to do electrochemical intercalation of lithium in titanium disulfide. And he succeeded and this is why he was awarded a Nobel Prize 2 years ago. However, when John Goodenough synthesized manganese and cobalt oxides, the voltage was much larger than the one of titanium disulfide, and titanium disulfide was a bit forgotten as we synthesize better and better cathodes for lithium systems. But as you may know, the research today is dedicated to go to post-lithium applications. So we try to use different types of ions, and especially at ICMAB, we are focused on calcium. Yes, calcium and magnesium. So in 2018, when I started my PhD, ICMAB just published a paper where they managed to do reversible electrochemical intercalation of calcium in titanium disulfide. And at that time, the state of the art was 100 degrees. However, the topic is evolving quite fast. And as you can see last year, they managed to do the same thing, but at room temperature. There is one little problem, however, is that calcium does not enter alone in the titanium disulfide. You also have solvent co-intercalation, and the solvent in question is propylene carbonate. So I'm going to explain quite fast. This is a schematic representation of a lithium versus titanium disulfide battery. And you have your electrolyte that is composed of lithium, an ion depending on the salt, and solvent molecules. So when you are discharging your battery, you will release one lithium ion as well as one electron. The electron will go through the electrical circuit, and the titanium disulfide will get reduced. To compensate this charge, one lithium ion will enter in the layers of the titanium disulfide, and you can actually see the change in the structural in the structure of the material with extra diffraction. So here I presented one pattern of the starting material, titanium disulfide, and one pattern at the end of the reduction, so with lithium intercalated. However, it's not always the case, and sometimes another chemical species enters as well. In our case, it's the solvent, propylene carbonate. And on the extra diffraction patterns, you have three very characteristic peaks of this new phase that is much larger. To do my studies, I didn't use ex situ experiment because it's very long to process. You need to prepare several batteries. You need to stop them at different moments of your charge or discharge. And then you need to open them to recollect your electrode material and to put them in the sample holder. So it's very long and time consuming. And you risk to alter your phase because of contamination, for example, with moisture. So I use an in situ cell that allows you to do the cycling and to collect patterns at the same time. So you do not have to handle your material, and you can collect many data with one single cell. However, as I told you, calcium, when I started my PhD, the state of the art with calcium was 100 degrees because calcium is a very slow system. So we needed a thermalized in situ cell that did not exist at this time. So my project was to develop this kind of cells. So we use this type of cell that is quite similar to the one we use for ex situ, but you can make extra diffraction on it. And coin cell that you may know this is a type of cell that is commercial, that is used commercially. However, calcium is a bit stubborn. Calcium ion is very slow, so it's easier to do a preliminary observation with lithium and then to report all what we have observed on calcium and to see if there are some differences. So in the first study, I used 4 different electrolyte salts and 3 very typical electrolyte solvents. Okay, let's dive into the results. So here I am comparing 2 cells. One with this electrolyte, which is a commercial electrolyte for lithium batteries. And here I have a different electrolyte where I added a little bit of propylene carbonate into the solvent mix. So let's compare both results. The first step of my cycling was to do nothing. I just collected a few patterns just to make sure there was no spontaneous evolution. Then I start to reducing the cell. In the first cell, you can see that the peaks are shifting toward lower angles as more lithium is intercalated between the layers of titanium disulfide. However, when the cell contains propylene carbonate, you see that you have the 3 characteristic peaks of the co-intercalation, and I represented both patterns at the end of the reduction, and you can see they are much more intense than the lithium intercalated phase. When you start reducing your cell, the peaks of the lithium intercalated phase shift back to their original position, but the co-intercalation remained unchanged. So this is irreversible. And we tried also to make a second reduction, but nothing was much different. You can continue to cycle on your material even if you have co-intercalation, but it's not reversible. It will always be here even if you try to cycle 5-6 cycles. So to understand a bit what is the triggering factor of the co-intercalation, we tested different electrolytes with different salt, different solvents. Here we fixed the solvent composition. It was ECPC, ethylene carbonate, propylene carbonate in the 50-50 ratio, and we use different salts. So as you can see, the capacity is not very impacted, neither is the X-ray diffraction pattern. So we concluded that it had no influence. However, if you fix the salt and you increase the quantity of PC in your electrolyte, you will have your capacity that is fading. And you also have some nice signature, electrochemical signature of the nucleation of the phase at the early stage of reduction. if you look at the X-ray diffraction pattern, you will see that the more you increase the quantity of propylene carbonate, the more the intensity of the co-intercalated phase is intense. So which means that as long as you can co-intercalate, you would co-intercalate solvents. So let's move on to calcium. We have understood that propylene carbonate was a triggering factor and it's irreversible. It happens when you start reducing your salt. So to summarize a bit the state of the art at that time, when I started my PhD, the state of the art was 100 degrees versus calcium metallic calcium, and using calcium BF4 electrolyte that Juan talked about yesterday. And as he explained, there's a lot of drawback using this system. So to optimize everything, the calcium battery, we replaced metallic calcium with activated carbon. And this time you can operate with different electrolytes and you can also operate at room temperature. So it's a great progress. Here, we tried to do it at moderate temperature. So we used our thermalized cell at 60 degrees, and we used activated carbon versus titanium disulfide cell. And as you can see, we can find again these 3 co-intercalation peaks, but you also have some additional peak. So let's have a closer look at the patterns. And you can see that at the early stage of the reduction, the first thing you see is a co-intercalation, but as you go a bit further, you will have a second peak here. Here the peaks are merged a bit, it's more clear here. But okay, the first phase to appear is the co-intercalation, just as lithium. And the second one is the intercalation of calcium, yes. So that only appears at the end of the reduction. Upon reoxidation, you lose the calcium intercalated phase, as you can see here. And the co-intercalated phase also loses intensity. However, we were not able to complete the reoxidation on this cell. So I present here another cell, which was cycled at room temperature. However, this time we were not able to get the calcium intercalated phase. We only have the co-intercalated one. But you can see that it grows during the reduction, and upon reoxidation, it disappears completely, and you retrieve your starting material.
Raphaelle, you have 2 minutes.
Okay, it's perfect. I'm doing the conclusion. So during this study, we highlighted properties from the co-intercalated phase. We know that it's triggered by propylene carbonate. The salt has little to no influence on this phase, but the quantity of propylene carbonate you put in the electrolyte will have an influence on the capacity and of how much co-intercalated phase you will produce. It is not a spontaneous process. You need to have electricity going through your battery to be able to build this co-intercalated phase. We have a difference between lithium and calcium. In lithium system, you have no way of removing the co-intercalated propylene carbonate, but with calcium, it seems to be quite reversible. And as a conclusion, we managed to reproduce part of the previous results because in one cell, we managed to do the calcium intercalation, but not to retrieve the starting material. And with another cell, we managed to have full reversibility on the co-intercalated phase, but not to have the calcium intercalated phase. So maybe one day we will be able to do both in situ. With this, I would like to thank my group from ALBA and ICMAB, and I would like to acknowledge the European Union for funding this project. And thank you for your kind attention.
Thank you, Raphaelle. Nice talk. Is there any raised hands in the audience in the seminar room? It's now time for the questions.
A question here in the room.
And here in the Zoom chat, I cannot see if there is any. Okay, sorry.
Hi, Raphaelle. Very nice, very interesting. It's nice to see how the project is advancing. Do you have, I know it's a very tricky question, but do you have any hypothesis on why PC intercalates and ethylene carbonate doesn't? or
Why it is a sorry,
yeah,
I didn't
like
get
when
the
you have a
question.
mixture of ethylene carbonate and propylene carbonate,
Yes.
like only propylene carbonate intercalates. Like why don't the ethylene carbonate does it?
Yes, it's true that the two molecules are very similar. We don't really know why, actually.
Okay, okay, so I just see if you had any idea. I know it's a tricky question. But
Yes, I mean, there were some studies that compare that with ethylene and propylene carbonate. There were quite a lot of difference, actually, not related all to the topic of co-intercalation. And there are several studies to try to understand why there is so much difference, why the molecules are very similar, but we don't know as for the co-intercalation why propylene carbonate intercalates and not ethylene carbonate.
Hi, Raphaelle. Congratulations on the progress you've made so far. I think it's a really nice work you're doing. I'm not sure if I understood clearly, but in slide 9, you said that you see some additional peaks. Can you tell me what is the reason behind observing the additional peaks?
On this slide?
Yeah.
Well,
right-hand
the
side
additional
diagram.
peak is because of the calcium intercalation. So the mechanism is a bit different than lithium, because in lithium you see the peak shifting because the structural change are not that major. When you intercalate calcium, you have to expand your lattice much larger than you have with lithium, and so you cannot actually see the peaks moving from the starting material. So you exchange one mole of electrons and bam, you've got the peak of the calcium phase. So actually here, so here is the co-intercalated phase, and just next to it is the calcium intercalated phase. So it means that you have inserted the calcium ion. This is what you want on a battery.
Okay. And in slide 4, you said you have used the solvent propyl titanate, or is that how you pronounce the solvent that you have used?
Propylene carbonate, PC if you want.
And okay. And why exactly you have used this solvent and not something?
That's a good question. I actually forgot to say it in my presentation, so thank you. We use propylene carbonate because the solvent used in that study of calcium was the electrolyte was calcium BF4 in PC. So this is why in lithium system we wanted to use the same solvents. We wanted also to try different solvents to see which one was triggering the co-intercalation. But originally we wanted really to have something very similar to the calcium system. And then we added more solvent and more salt to test and to understand a bit better.
Thank you. Thanks a lot.
Thank you, Raphaelle. I have a question, but if you don't mind, I'm gonna email you.
As you want.
Yeah, because it's more of my interest. So I think maybe I can email you just to ask. It's about the room temperatures with the different atmospheric conditions that you showed. So maybe I'm gonna email you and then we can discuss a bit. Okay.
Okay.
Thank you very much. So continuing the program, we are going to continue with the next speaker. His name is Mohammed Khaliq. He was born in Pakistan, and he has bachelor and master from the Islamia University of Bahawalpur. I'm sorry, the bad Pakistani, and the GC University in Lahore, respectively, in physics. Nowadays, he's working now by synchrotron and with the partner in the University of Barcelona under the project Gigahertz Magnetization Dynamics at XPM. So, Mohammed, whenever you are ready, the floor is yours.
Can you hear me? All right. Thank you for the introduction. My name is Khaliq, as you all know, and this is the topic which I'm doing PhD on. It is gigahertz magnetization dynamics in X-ray photoemission electron microscope. So I'm actually doing PhD in a group of condensed matter physics at Alba Synchrotron and University of Barcelona. So my supervisors are from these two institutes. Well, I will just tell about the highlights, introduce that what I'm doing and what I'm going to do. It's the just outline, and these are the things which are still going on or pending. So I'm working on these things currently, and the above all things which have already been done, and yeah, I'm proceeding on that. So in order to work with this X-ray photoemission electron microscope, you first get to know that what it is actually and how it works at the Alba Synchrotron facility. So for that, it's a really state-of-art facility for visualizing the magnetization dynamics at quite small and fast time scales. So this is, I think you can see, this is the photoemission electron microscope. It has different regions. Actually, this is the main chamber where we do the experiments, and these are the different chambers from in which we put some samples to do some any kind of characterization, or you want to sputter the sample with any gases, so we do that here. About the operation, so in order to work there, as I told you, we had to know the technical knowledge of how it works, what is the what kind of samples we use, and what are the approaches for different experiments. Like if you want to do with the high frequency, if you want to do with the deal with the electrical signals to the samples, or for that. So we have different kind of samples for that. Okay, this is actually we use how do we see the magnetization dynamics in the material, or magnetic behavior in the films or in material. So for example, consider this, that we have a film, we have these X-rays coming which are incident on the sample, and then we have an objective lens from where to at the high voltage the electrons leave the sample and strike to the to go to the lens, and then from there we can see, as you can see here, this is actually the PM image, and then after analysis we get this XMCD image. So in this way we get the XMCD image, which tells us about the magnetization states or magnetization behavior of the sample yes. So in this, there we use different kind of sample holders. You can see here this is in plane, in which we can apply magnetic fields in plane of the sample. Here, this is the quadrupole from which we can apply the magnetic field in any direction. These are the special, this is the out of plane sample holder, in which we just apply the magnetic field in the out of plane, and this one as well. About this one, this is the special sample holder in which we use PCB. PCB is printed circuit board, which we connect the sample to apply signals, electrical signals or something, electrical signal to the sample. So we use these kind of sample holder, and we use PCB on which we mount the sample and connect this. Yes. So why magnetization dynamics? You know, as all you know, that it is the magnetic. There are two types of magnetic material which are important, which is ferromagnet and antiferromagnets, and you all know that ferromagnets have domains which are aligned parallel, and in antiferromagnets it's aligned in a opposite direction. So the applications, we have wide range of applications for the magnetic material. As you know, that we are using all in every devices we are using, and in the future devices we are for the transfer of the signal communication, and for those purposes we are using these magnetic materials. And depending upon what kind of static dynamic states, static state of magnetization and dynamic state of magnetization depends that what do you want to do, high speed, low power signal processing devices, or what kind of devices you want to prepare. So the reported research work is like they have been already doing, actually the gigahertz magnetization dynamics is a vast it's a vast field. Like, there are different kind of processes that takes place, and this is among one of them, that in which we control actually the magnetization dynamics of the material with the surface acoustic waves. Like, why we are doing this? Because it's a low power control of magnetic states. For the other materials, if we want to change the magnetic states, for that we need to apply the magnetic field, and which causes, different ohmic losses or different kind of temperature for that. But in this case, with the surface acoustic waves, we can control the magnetic states as well. So, and magnetoelastic effect has been observed in ferromagnetic material due to surface acoustic waves. Then another work is like for signal transmission for the communication. Another experiment, another paper has been reported in which we can see the nickel surface acoustic waves observation on lithium niobate. Actually, this is the piezoelectric material, and that converts generates the surface spin waves in the ferromagnet material and it changed the magnetization dynamics, and which you see here at zero magnetic field, we don't see the rise of the spin waves. But here at 15 millitesla, when we apply the magnetic field, we see quite strong spin waves motion, the waves. So yeah, we see the propagation, and then but the thing is that when we apply the magnetic field, we have magnetic field and more damping we face, and due to which there's a temperature and there are losses. So that's why we are moving towards the surface acoustic waves. So the limitation which were there already, that in the ferro materials usually have intrinsic damping, and for that purposes in the previous experiment here, they have used 500 megahertz frequencies. They excite the sample at 500 megahertz frequencies through IDTs, and then that generates surface acoustic wave in the lithium niobate, which is piezoelectric, and that generates the spin waves here. So, but its range is quite small, up to 15 millimeter, 25 millimeter, it was recorded. But we want to increase this limitation, increase this limit. So ferromagnetic materials has intrinsic damping for sure, and due to which the resonance effect is quite low. Effects are in gigahertz regimes. So, and our system, which is in the PEAM, usually due to this DC connection in the XPEAM facilities, we can reach up to only hundreds of megahertz, and hence the measuring magnetic non-resonant. So actually, we are not actually measuring magnetization dynamics at the intrinsic frequency of the ferromagnetic material. We are just doing on the non-resonant magnetic excitations. So this was my objective, that to control the spin waves with the propagation of SAW, using the flow for the functional magnetic devices, which are the future of devices. And there are then two sub goals in which I have to, first I will generate and detect the spin waves in ferromagnet materials at frequencies greater than 1 gigahertz using the XPEAM to observe them, because it is only, and then I will do the acoustic manipulation with the surface acoustic waves with this, not only the magnetic ferromagnets, but also Heusler-Rosen magnetic oxide, like antiferromagnets and these kind. So for that, I proposed two strategies, which first, that as I told you that with the XPEAM, it was not possible to reach more than 2 gigahertz, into gigahertz regime frequency. So for that, we had to design some setup which can actually reach to higher magnetic fields, higher frequencies, and then applying SAW to intrinsic. So we applied SAW with the frequencies that are actually intrinsic resonant frequencies of the material. And then we will excite the spin waves at higher amplitude. So this was the goal. And these are the two methodologies which I explained, that this is the sample, these will be the films which I'm going to prepare, and we'll excite this and we will see the spin waves. And then this is the second goal, which I'm going to do in this way. So this is the schematic of the new actually technical development we had to do, and my last year was being devoted totally to this thing, because yeah, you have to develop the technical, you have to develop the setup which can which could be compatible with the existing XPEAM setup. So for that, we developed the system. As you can see, it has different parts, and with this thing, we had to develop more different sample holders. And this is this part is actually this one here. So which can actually connect with the sample and provide the signals. And for this, we had to design different sample PCBs and connect these SMP connectors so that they can connect to this. And yeah, this is here, you can see how the connection scheme works of the sample inside the beam. And then this is the high frequency setup, the real view at the beam station connection point. So yeah, we had to do, from here, we actually supply the external signal from here, which is connected to the wire here, and this apply high frequency signal to the sample. And this is actually this SMA connectors. And then it can be pressed, this can be pressed, and which can bring the sample, which can bring this thing to the sample stage, because we cannot move this sample stage main manipulator inside the beam towards this. So we had to move this, and we have connected them. We have faced a lot of problems here. So it looks like easy, but then we had to test it, and things were not working. Like sometimes this was broken, the wires were not okay. So it takes time, and then we had to deal with that also. So these, we didn't test this high frequency stage. And then when we tested it at some frequencies up to, because previously it has been tested up to 500 megahertz, but this with a new setup that either it's working or no, then we tested it, and we can see that you can see the waves on lithium niobate. It's just a test to see that if it's working or not. So at 750 megahertz, we can see the waves, and then at 875, it decreases the wavelength, and then at 1 gigahertz, it decreases as well. So this was the test of the high frequency state, that it's working or not. And then the thing is that this high frequency setup has been registered as a patent, and the Office of Spain, Patents and Markers, with this last year, it has been registered as a patent. So yeah. So the experiments, now we are extending our experiments to piezoelectric substrates as well, and different piezoelectric substrates and because previously we have been using lithium niobate, and with different antiferromagnetic thin films. But why magnets? Because they don't have known magnetization, they don't have net magnetization, because their dipoles are actually, the magnetic moments are opposite, so they cancel. The stray fields are absent. That's why they don't have, like, when you put the magnetic field, they react, but you have to overcome that, the magnetic field force. So this is not, and then it will be sensitive to external perturbation. So antiferromagnetic domains have been controlled by electric currents already. That has been reported. But we want to see the magnetoelastic effect as an alternative to control antiferromagnetic domains, because it has been more easy thing and more, less energetic. It causes less energy as compared to the electric current, because electric currents can cause the current or the magnetic field, and that generates, the different ohmic losses and different kinds. So we tried this this technique on this to control antiferromagnetic domains with this, which has already been done on lithium ferromagnetic materials. So the purpose of this was imaging source in antiferromagnets to control antiferromagnetic domains. This was the first our goal. Then measure the delay with respect to the source trains. That has been done already with the ferromagnetic material. So we want to see that if it's possible in the antiferromagnetic domains as well, that, and if it's faster than the ferromagnetic domains as well. So these are the domains. You can see we have just done this recently experiment, and we see here some domains. Okay, we can see only antiferromagnetic domains, and this thing is still going on. So we haven't not been completed because I've been doing the analysis, and then the school came. So I'm just showing you the result which I can do the analysis. So I'm sorry. So this is actually here. This is the gallium arsenide. This is the piezoelectric material on which we deposited here. This is copper manganese arsenide. This is the antiferromagnet, and this is the another piezoelectric material. So here we draw line width profile, and we see the waves. Okay, this is actually not actual scale, which I show here in the big counts. It's just a rough thing. So the wavelength, which in pixels I'm showing here, which is equal to more or less 160 pixels. If you, sometimes you will find it out. So then we, And then these are the profiles of the antiferromagnetic materials on which we draw the line width on the same, on different phases with different phases of the wave at different or the same places. And then we see that, okay, if it's, we can see the spin waves in this antiferromagnetic material or not. But we see here, and then after subtraction and clearing the background, we obtain a really good curves, and which corresponds to the same as it was observed in the piezoelectric material, gallium arsenide. But still, we have correlation with that, but still we are looking for the other things, that if it is consistent, this wavelength, this wave is consistent and with the rotation of the sample as compared to the beam and the beam of the X-rays, and at different points, that if it's consistent or not. So this is still in process. So secondment. So I'm going to spend the secondment in Norway. Why Norway? Because the group which I'm in contact with, they are quite experienced in preparing a new materials on the lithium niobate, because they are experienced in that, and they have, it's quite difficult to prepare those films on the lithium niobate surface. So that's why I'm those. But why those specific films? I'm not going to tell here, but if you want, I will tell you later when I'm going to do that. Why these films? Because they are attractive material for the spin torque and spin transfer applications, and they have low saturation magnetization as compared to the nickel or other ferromagnetic materials, and they have lower magnetic damping as compared to other, and narrow resonance spectrum, which leads to higher, the spin waves excitation with the greater amplitude. So we can see there are more effects in that. So for that,
sorry, you have 1 minute, okay?
So this is the beam time which has been accepted in the proposal call, which we have presented, and it's going to take place in December. For that, we had to prepare the samples, and then we do. So these are the different experimental contribution which I've been doing in that, which has been published as well. This is in the process, and yeah, and then the users are going to exploit that high frequency setup for different experiments, and that have been accepted for the beam times as well. So this is the team from the ELBA. This is my principal supervisor. This is my co-supervisor from University of Barcelona. And these are the guy. And these are the people who supported, who really give me advanced supportive hand on development of this high frequency setup, which was not easy. And then the electronics team for the cable and these connections. And in the end, I would like to thank European Commission, Government of Spain, DocFam, and ICMAB for giving me this opportunity to perform this experiment and activities, and I hope I will accomplish in that. Thank you so much.
Thank you, Mohammed. Congratulations for your work. It's really interesting. So let's start with the seminar room. Any questions?
We have a question here.
Thanks. Really nice presentation. I would like to ask something regarding the slide 5, where you say that the spin waves are very prominent in 15 MT,
Yes.
and not at all in.
No, they are prominent in 0 millitesla as well. Yeah.
Okay, but comparatively, it's more, no? In
Yeah.
15. But do you know? Can you tell us the reason why it is?
Because when we apply the magnetic field, we align the spin waves in the domains in the direction, in a particular direction, and they turn them, which increase the spin waves amplitude. And because of that, we can see with the magnetic field, increasing magnetic field, we can see a clear, oscillation in the ferromagnetic material. So that is the reason, and that's why we want. But there are, different things: the damping, the increase of temperature because of the magnetic field. So that's why we want to overcome this thing and use some other material, which I'm going to do in my secondments, prepare the films to overcome this heating and other effects.
Okay, and related to this question, you say also in slide 6, you have a limitation in the first point, which the intrinsic damping is very high. So this is what you're going to carry out? I mean, how are you going to plan
Exactly.
to
It
modify
has intrinsic damping quite high. So we are sorry, is this a question or there's another? Okay.
I just
okay.
want to know how you're trying to modify this fallacy, you know?
This thing, actually, the thing is that we are going to apply we are going to excite the intrinsic resonance frequency of the ferromagnetic material. Okay, with a magnetic field. We do it outside, and then we are going to match the higher the frequency of that intrinsic resonant frequency of the sample and apply the signal on the same frequency. So if you see, like, for example, this is the spinning of the thing, okay, precision, this is the precision. And when you precise, like in not matching frequency, it will not give the high amplitude, and it will precise, it will do the damping quite fast. But if you do the precision with the same frequency, then it will be for precise for longer time, and the damping will be low. So this is our plan to do in this thing.
And this technique is available in where you are going to do the secondment, right?
No, this technique is already been done. You can do, because with the ferromagnetic material, we have been doing that, but at 500 megahertz frequency. Now we want to increase it. But why? Because I'm going to prepare those films that has higher low saturation magnetization and low damping as well. So that material I'm going to prepare. With this material, we are dealing with that 500 megahertz already we have been done, because it matches the specific frequency of the Alba synchrotron with which the light, it circulates. So we are doing that with a multiple of that frequencies, and we excite the samples up to 500 megahertz because these are matching with that. But now we are moving to the gigahertz, because that we will not face this damping problem, and the precision will be greater, and the amplitude will be greater, and the propagation of the waves will be greater as well. So that's why we are doing that.
Okay.
And to go and about the secondments, the material that I'm going to prepare, they have experience of developing those materials on the lithium niobate surfaces.
Okay.
So that's why I'm going there, because it's quite difficult. It's not easy. So we are going there, and then we will see.
Okay. Good luck for your second.
Thank you so much.
Thank you. Is there any other question? Because we are running out of the time. We need to go for the next speaker.
One more question we have here.
Maybe they can discuss later because we are passing the time.
All right.
Yeah, no problem.
We have time today because we have 1 hour and a half for talks. So maybe.
Okay. I thought it was only 1 hour. So okay.
Okay, thanks for granting me the question. Can you tell us something about the surface sensitivity of your technique?
Sorry, surface?
Sensitivity of your technique. Is it surface sensitive?
Surface sensitive, yes, I would say, because these are only, the surface acoustic waves only work on the sample surface, and these develop, the tensile strain. These develop the strain, and due to which it causes the generation of the spin waves in the adjacent ferromagnetic layer. So it's a surface sensitive thing. Yeah.
Exactly, it's what I was thinking, because you're shooting X-rays on the samples, right? And they don't penetrate the sample very deep. And also, according those lines, do you prepare your samples in situ and then you measure them? Because I did also photoemission spectroscopy in my master thesis, and we had the problem when we prepared the samples somewhere, took them to the normal atmosphere, an oxide layer would grow on top, and if we then try to measure them in the PES, we don't see the intrinsic signal of the sample. We actually see the oxide. So do you have similar problems?
No, we don't have actually these kind of problems, because the method of preparation, actually I've been last year focused on this development of the high frequency setup, and now I'm going to focus on the preparation of this sample things. So the samples we are already having, the people they are doing, we don't have any problem of this oxide things, because we have already done the XAS. We do the X-ray absorption spectroscopy before analyzing the samples, and before analyzing our samples or taking the measurements, and we don't see any kind of these oxidation layers. So yeah.
All right. Thanks.
Thank you.
Good luck.
Thank you.
Thank you very much. The presentation, also answered the questions so well. For the next, can we move on, or is there any other question in the room?
Yes, we can move on.
Yeah, okay. So the next speaker, it's Artur Romanov. He has bachelor and master. He has done his bachelor and master at the Physical Institute of R8TH in Aachen University. Nowadays, he is at ICMAB under the supervision of Dr. Joffre Gutierrez and Professor Teresa Puig. And his title of the thesis is the Ultra-High Field Conductors for Accelerators Physics. Artur, whenever you are ready, you can start. The floor is yours. You have 50 minutes.
Can I see the title of the presentation, please? No.
It's not shared from the.
Yes, this is
Zoom.
perfect.
Yes, 1 second, please.
Yeah, that's the correct one. Perfect, thanks a lot. Okay, Marita, thanks for the introduction. Yeah, for those of you who don't know, I'm a physicist and I'm in my last 3 months of my PhD actually. And it is, I'm part of the superconducting materials and large scale nanostructures group at the ICMAB. And my work is conducted within a quite big consortium consisting of the Polytechnical University of Barcelona, Alba Synchrotron, ICMAB, and CERN. And yeah, today I want to talk about how we want to use high temperature superconducting tapes for the future circular collider. This title might sound cryptic to you, but I will do my best to explain you the terms in the following. So to understand what superconductors are, we should probably start with the electrical resistance. The electrical resistance is the amount of the dissipation that electrons see when they are conducted through an object, okay? And in the common knowledge, the material class with the lowest resistance are metals, for example, gold, silver, copper. They don't only have a low resistance, but the temperature behavior of the resistance is also very specific. It decreases with temperature until it reaches a finite value at absolute zero. Now you can ask, can the nature do better? How low can we go with the resistance? Well, in the beginning of the 20th century, Dutch scientists measured the resistance of mercury at very low temperatures. He saw first metallic behavior, but then something super weird happened. The resistance dropped to absolute zero. So it's a perfect conductor. Nobody believed him in the beginning. They were thinking, okay, he cannot measure the resistance correctly. But after a while, other laboratories also confirmed this result, and it was the birthday of the superconductors. They don't only have perfect conductivity, but the second important property is also that they expulse the magnetic field from its interior. Unfortunately, all of this comes with a little caveat, because in order to have these super nice properties, you need to cool the material down to very low temperatures. Low temperature superconductors need liquid helium to become superconductive, and liquid helium is not abundant and it's rather expensive to produce. Luckily, about 35 years ago, high temperature superconductors were invented. Unfortunately, by high temperature, I don't mean 30 degrees or something like we have right now. I mean minus 200 degrees Celsius. But the good thing is you can use liquid nitrogen to cool them down to get to the superconducting state, and this is way more cheaper. Now, the most prominent candidate here is probably YBCO, which is a ceramic, and it has a perovskite-like crystal structure. The applications of superconductors are wide. The most famous one are probably large field magnets, which are also used for magnetic resonance imaging. But today I want to talk about how we can use superconductors in the beam screen of accelerators. The largest particle accelerator in the world is today the Large Hadron Collider. It has a circumference of 27 kilometers and it is based in Geneva. In fact, it is also the largest microscope in the world because we are able to probe with this device even quarks, so the building blocks of elementary particles like protons or electrons. No, electrons not. Well, the biggest accomplishment of this device was probably the experimental confirmation of the Higgs boson in 2012, which explains how particles receive their mass. 1 year later, this was awarded with the Nobel Prize. Now, in order to continue the success in particle physics, the European Organization for Nuclear Research, CERN, is planning to build a next generation particle accelerator. There are several different possibilities that they think about, but the most ambitious scenario is represented by the Future Circular Collider. It's also a ring collider. It will have circumference by a factor of 4 bigger than the LHC. The dipole fields will be bigger by a factor of 2, and the center of mass energy, so the collision energies, will be then 8 times bigger than in the LHC possible. With these increased energies, the community hopes to shed new light on phenomena like dark matter, supersymmetry, or the origin of the neutrino mass. With this, it would help us to understand the Big Bang better or the expansion of the universe. It's a monumental project, as you can imagine, because this 100-kilometer ring will be of 6-meter diameter and 100 meters below the Earth. So it has to be built. And the building and the operational phase is already scheduled for the next 70 years. And it will be a very expensive project. Roughly, it is estimated to be of 27 billion euros. Now, more than 130 institutes have to want to check if building the FCC is actually a good idea. Is it feasible? Can we make it an efficient and a sustainable particle accelerator? This is also part of my thesis. And as I already mentioned, we want to use these superconductors, high temperature superconductors, as a beam screen coating. What a beam screen is, I explain the following. For this, we have to take a look at the cross-section of such a particle accelerator. If you want to collide particles with each other, you need to accelerate them into opposite directions. Since they are on a circular track, they will emit synchrotron radiation, which is problematic because you have these steering magnets at its vicinity, which are held at very low temperatures. So if you will irradiate them with the synchrotron radiation, they will heat up too quickly, quench, and get damaged. To prevent this, engineers introduce these stainless steel beams, which are called beam screen chambers. Okay, so as I already mentioned, the purpose is to thermally shield the cold pores of the dipole magnets from the synchrotron radiation emitted by the charged particles. Now, since the stainless steel pipe is so close to the protons, mirror charges will be introduced into the stainless steel beam pipe, and they will interact electromagnetically with the protons, which can cause beam instabilities. This cannot happen. For this reason, highly conductive materials are introduced in its interior. For the Large Hadron Collider, copper is in use. It offers a low enough resistance. However, as I mentioned, for the Future Circular Collider, the energies will be bigger. The synchrotron radiation will be bigger, and thus you have to increase the temperature, of the operational temperature of such a beam screen chamber, and that this temperature, the resistance, the surface resistance of copper might not be low enough to guarantee a stable beam. For this reason, we propose to use coated conductors instead. It is basically the high temperature superconductor that I was talking about, YBCO, but it is on top of a flexible substrate, so it makes it more applicable for any kind of applications, okay? And it's also protected. So the goal of my thesis was to evaluate if these kind of coat conductors can be used as a good beam screen coating for the Future Circular Collider. And now I come to the results, so to the actual requirements that we have to test the coat conductors. one of the requirements are it has to sustain the peak currents of 25 amps introduced by the mirror charges. As you can imagine, these proton bunches, they don't consist only of 3 protons. In fact, in an 8 centimeter bunch, there are 10 to the 11 protons, which circulate with almost a speed of light around this, the collider. And thus, the mirror charges will be quite high. A superconductor cannot sustain infinite amount of large currents. And that's why we measured the actual critical current. So the current at which the superconductor transits from the superconducting into the normal state. We measured it as a function of magnetic field for several cold conductors. There are 2 things I want to point out. First, it seems like at 16 Tesla, so this is the operational magnetic field in the FC, or the maximum magnetic field, the cold conductors will most likely be above the 25 amps of the induced peak currents. Second, although all these cold conductors, they have REPCO, they use REPCO as a superconductor, the field behavior is quite different. So we found a link between the microstructure and the actual performance of the superconductor. So depending on the microstructure of your superconductor, you can have better or worse performances. This is quite exciting because it opens up for material engineers the potential to tailor your superconductor for specific applications. I mentioned copper is being used in the Large Hadron Collider, so it's a direct competitor of superconductors. That's why we had to measure the surface resistance as a function of magnetic field of copper in comparison with several cold conductors. You might be surprised here, why do we see suddenly a resistance for superconductors? Well, it's not the normal resistance, it's the surface resistance. As I mentioned, or maybe I didn't mention it, but the mirror charges, they oscillate with a very high frequency, around 1 gigahertz, and thus dissipation occurs. Only in the regime of direct current, the superconductors don't have dissipation. Actually, in high frequencies, they do have a resistance. But we see up to 9 Tesla and 8 gigahertz, the coated conductors perform better than copper. So good news. Superconductors are preferred here for this case. The second thing, again, we see link between the microstructure and the performance of superconductors. If you introduce, for example, pinning centers like VZO, nanorods, nanoparticles, or you even try to incline the z-axis of your superconductors, the performance in field becomes better. So again, a clear correlation between the surface resistance or surface impedance even, and the microstructure of the superconductor. I want to mention that we measured it at higher frequencies than actually necessary for the FCC. The FCC would only have mirror currents up to 1 gigahertz. That's why we wanted to model the field behavior of the surface resistance with a Gittelman-Rosenblum model and extract vortex parameters in order to extrapolate the surface resistance which we would expect to measure at FCC conditions. And this is what we did. We fitted the field behavior. From this, we determined the pinning frequency and the vortex viscosity, and this allowed us to now estimate the surface impedance at FCC conditions, so at lower frequency and at higher magnetic fields. In fact, at these conditions, we expect to outperform copper even further. While at 8 gigahertz, some of the cold conductors were only by a factor of 4 smaller in terms of surface resistance than copper. At FCC conditions, they are sometimes even by a factor of 70 smaller than copper in terms of surface resistance again, while the surface reactance is in a similar range. We found during the last years also, or we demonstrated during the last years also other important properties like the compatibility with the field quality in the beam screen chamber, the compatibility with the vacuum requirements. And we also found a technique which is potentially suitable for large scale applications sorry, it's a coating technique which is potentially suitable for large-scale applications, and it's not destructive. So we are actually able to attach the coat conductor to the beam screen chamber without damaging it, which was also an important challenge to overcome.
Artur, you have 2 minutes.
Perfect, I'm almost done. Now coming again to the question of the beginning, is building the FCC feasible? I cannot tell for sure yet, but what I can tell is that our generated results, they promote further investigation of considering coated conductors as a potential beam screen coating alternative to copper for a more sustainable and efficient future circular collider. Okay, I would like to acknowledge all my collaborators and the funders, of course. And yeah, also my supervisors, Teresa Puig and Joffrey Gutierrez, and all the rest of the SUNAM group. Yeah, and you for your attention. Thank you.
Thank you very much, Artur, for the nice talk. Let's start with the seminary room. If someone has a question. Is there?
No questions in the room, but Nikki has a question on Zoom.
Yeah, okay. Nikki, you can turn on your camera and your microphone.
Hello, thank you very much, Artur, for the very nice presentation. So I learned even something new from this. I would like to ask I think that was in slide 9, where you said that the surface reactance of CCs and copper is quite similar. Can you elaborate on this, please?
Yes, so I maybe should have mentioned that when I give this values, these figures of the surface resistance is 15 to 70 times smaller, I mean always the values at 16 Tesla, okay? And if you now compare the surface reactance of the coat conductors, these are the dashed lines, I didn't mention it, with the surface reactance of the copper, these are the stars, you can see that they are always in the same order of magnitude, right? At small fields, the coat conductors have a lower surface reactance. At higher fields, they are slightly higher, maybe by a factor of 2 to 3, but they're in the same order of magnitude. However, if you look at the surface resistance, we outperform with the coat conductors the copper at least by 1 order of magnitude, close to 2 orders of magnitude. So this is still beneficial it is still beneficial to use coat conductors as compared to copper for the beam screen coating in this sense.
This surface reactance, you obtain it from extrapolation, or if I'm
exactly
correct?
This is
Okay,
not measurement data, this is extrapolations. So we, as I mentioned, we determined surface vortex motion parameters, so the pitting frequency, the vortex motion, also the Labusch parameter, which tells us how the superconductor behaves under an radio frequency magnetic field excitation. Okay, we measured it only at one specific frequency at 8 gigahertz and only up to 9 Tesla, but we can estimate some errors on these values, and with this we, I think, can more or less confidently estimate what surface impedance you would expect at other conditions, which are still in the regime of the model that we are using. Of course, it's a single vortex motion regime.
Lastly, sorry, I noticed some deviation of the curve at 70 Kelvin with the Gentleman-Rosenblum model.
So this deviation, you mean?
Yes.
Right, you're right. So
where do you think this come from?
Yeah, at lower temperatures, we can describe the data quite well with the model. Okay, the model is the solid lines and the measurements are the markers. However, starting from 50 Kelvin and higher temperatures, we see a slight deviation, especially at high fields. I think this can come from 2 different things. First, our model doesn't include flux creep, so no thermal effects are included. That's why it's kind of natural that we deviate slightly from the model at higher temperatures. And second, we might also approach the upper critical field for some superconductors at higher temperatures at 9 Tesla. And this is also not considered in the model, and that's why we see a deviation from the model.
Okay, thank you. Because it's like, it's very important, no? Because if I'm the one who will look at it, the deviation starts at 40, and we operate at 50.
Right.
And we operate at 50, so it's like very important to.
Totally. You will, with your multimode resonator, you will have, you can somehow determine or fix more
the flux creep factor
of freedom, and one of these can be the flux creep. In fact, you can include it in the model for sure.
Yeah. Okay. Thanks. That's all from my side.
Thanks.
We have another question here in the room.
Okay.
Hi, Artur. Really nice work. Looks very promising. It's completely different from my field though. But in slide 6, you say you have different coded conductors of different magnetic fields, right?
I show the critical current as a function of magnetic field for several code conductors.
I just want to know, why are they so different from each other? How is it?
Yeah, maybe I should have lost a bit more words on it. As I mentioned previously, they are all REBCO, so rare earth barium copper oxide superconductors. And in fact, we are only probing the superconductor, not the metallic substrate or anything, because it's again a surface sensitive technique. However, the microstructure of all the code conductors is quite different, because also the growth techniques of all the code conductors is different. The entire architecture is different. They might use different buffer layer templates. They might use different growth temperatures. Sometimes they use different substrates, and all of this, or they use even different precursors. And all of this influences, of course, the growth of a material. So the lattice parameters are slightly different. Sometimes they have some other materials incorporated, as I said, like some barium zirconate or barium hafnate nanoparticles. And this all influences also the actual pinning behavior of the material. And this is what we actually see. We see the pinning behavior of our materials.
Okay. That explains my question. Thank you.
Thanks.
Thank you. If there is no further questions, we can move on to the next speaker. The next speaker is Tandava. He is from India, graduated with Master in Analytical Chemistry. Nowadays, he's at IREC, the Institute of Research in Energy of Catalonia, under the supervision of Professor Morant and Dr. Sebastian Murcia. His project has the title of Advanced Catalyst Materials and System for Electroconversion of CO2. Tandava, whenever you are ready, you can start, okay?
Yep.
Thank you. You have 50 minutes.
Good morning, everyone. Today, I would like to present my ongoing thesis project. It's Advanced Catalyst Materials on Systems for the electroconversion of CO2. Right now, I'm working under the supervision of Dr. Joan Ramon Morante in the Energy Storage and Catalysis Group, and under the co-supervision of Dr. Sebastian Murcia at Catalonia Institute for Energy Research, IREC. And then, so why do we need to see it like in terms of greenhouse emissions? So we have almost like 65% of carbon dioxide emissions, and which are coming from the fossil fuel usage or from the industrial process, and then only like 11% from the forestation, and then from the other forms, like we have the remaining 20 or 30%. So then my point is like, why do we have to? How do we have to use the carbon dioxide we have? So then we can use it for the reduction to alternative fuels. We have different process available, like many people are exploring right from the beginning. So it can be electrochemical, photoelectrochemical, and thermal catalysis, and photothermal and photocatalysis. But right now, my current focus is on electrochemical and photoelectrochemical. But exact focus is on electrochemical now. So I'm sorry. This electrochemical CO2 reduction can be done using two type of cells. This is an advanced flow cell setup, which is like this, having flow fields, and then a simple conventional head cell. And then whatever the cell I use, the main idea is having a simple cathode and anode with an ionization membrane in between, which allows the ions to move from cathode to anode, or anode to cathode. So where the CO2 is fed to the cathode chamber, and then we have, when a current or potential is applied to the cathode, we have the electron transfer mechanism, and then from the CO2 we have products from the reaction intermediate CO. The movement of ions is from through the membrane, and then at the anode we have the oxygen evolution reaction, which is quite common. And we also have a hydrogen evolution reaction at the cathode, which is quite competitive, or we can call it as a poisonous reaction or unwanted reaction at the cathode, which we are not looking at. And then, but why do we need to do this? So my point is very simple. Since the time of industrial revolution, we are too much dependent on the fossil fuels. And then we are like, we have, as I showed in the first slide, we have enormous amounts of CO2 in the atmosphere. So what we can do is, as I said, by reducing it to alternative fuels. So we can take the CO2 from the atmosphere. We can, already many groups are working on the carbon capture and sequestration. And then we can use the renewable energy sources that we already have, or we are using right now. And then we can deploy them in the advanced flow, in the electrochemical cells. And we can make them react using the, having the cathodes, by deploying new novel materials there. And then we can have this alternative fuels, like this is ethylene and ethanol, methane, and say carbon monoxide. So my initial point is ethylene. So what do we have, like with this? If we are having these renewable fuels, maybe we can move to a faster or like sustainable environment. This is the whole idea to attain the carbon neutral economy that we can, that is proposed to reach in the next 50 or 100 years, maybe, hopefully. So, but why ethylene? Why ethylene is required? If you see the market prices, the price for the ethylene is very good. The price per metric tons is like quite expensive than the other ones. So there is plenty of chance to explore things here. But also, if you see the carbon emissions and the global market sizes of different products that we obtain from electrochemical CO2 reduction or from any other types of CO2 reduction, the place for ethanol or like C2 or C2 plus products like ethylene, there is a plenty of scope, and it can be a like attractive target for the reduction of emissions that we already have. So, and if we have, this is like a summary of different works proposed from almost like 1986 to 2019. So if you see the function of current densities towards like with the Faraday efficiencies, we are reaching almost like a bit more than 60% Faraday efficiency, and the current densities of almost like 150. That's these are the partial current densities for ethylene, which is like, and what we can see is the green chamber here, like we have a plenty of room to explore. And also if you see the energy efficiencies, it's quite, we are reaching almost 50%, that's quite a good number, but we still have a plenty of scope. That's why ethylene can be a very good option, and it can be levelized, according to the levelized market cost, it's a very good viable thing, because most of the times like ethylene is a precursor for many of the plastic products we use, and most of the ethylene is produced by cracking the crude oil. So we are mostly dependent on the fossil fuels. So in this aspect, if we can produce ethylene using some electrochemical CO2 reduction or any other types of CO2 reductions, that is of a great importance, or we can have a major breakthrough. Many people are working on this. And then, so we know we need ethylene, but how can we get ethylene? So when we go to the, when we go to the periodic table and see for different atoms or different elements, so we have different, different type of elements. All the transition elements are very good for production of hydrogen evolution reaction. And then we have these cadmium, indium, these metals which are good for the formates or the formic acid products. And then the palladium, silver, or the aurum, like gold, like gold, like noble metals, they are good for the carbon monoxide. There is a mistake here, so don't know. And then we have only copper, which is actually good for the hydrocarbons. Hydrocarbons are having more number of carbon atoms, like ethylene, ethanol, propanol, butanol. Many people are producing more than C3 products also. So this is like, we have the copper, but why copper is only good for ethylene? So when we see already there is a plenty of research has been done since now, like almost from 1985 by Julio and all. So which can be, it's good for hydrocarbons like ethylene, methane, ethanol. But why do we need it? When we take it to the metal classification, here we have, it is the only promising metal that can promote the electron transfer reactions of greater than 2 electrons. And then when we see the adsorption isotherms, it is the only metal that found to have a very positive adsorption energy for hydrogen and a negative adsorption energy for carbon monoxide. So maybe as a CO is a key intermediate in forming the next steps or next products in the CO2 direction, I think copper is is found to be the good or most promising material, or we can call it as a benchmark material. So I think copper is a very good copper is a very good material to focus on. So what do we do with the copper? So what do I do with the copper? So I have this advanced form of electrochemical cell, and this is the cathode I'm working on with. So these are the gas diffusion electrodes that I deploy here in the cathode, the current collector. So the CO2 passes from here through the catholyte, and the catholyte is also passed through a peristaltic pump. So the idea of this is to have a gas diffusion electrode as a cathode. So the gas diffusion electrode can be this can be like a scheme like this. So it can be with so gas flows from this side, and then it has a microporous layer or substrate. Substrate can be a carbon torre, like a simple carbon paper with without or with hydrophobic effect, and then it can be a copper foam. So the main principle is like gas flows from this side, and we have the microporous layer as a carbon as a microporous layer, and the catalyst nanoparticles, copper, the one that I'm working on. And here we have the liquid electrolyte that comes all the way like this. So the main idea of having gas diffusion electrode is it should allow the gas to pass through from one side, but because of its hydrophobic nature, we can avoid electrolyte moving back to the electrode and making like flooding of the gas diffusion electrode or something. So we can have a very good catalyst layer here, and then maybe we can develop the hydrophobic effect by deploying some PTFE or some ionomer based things like that I'm using now, Nafion or Fumeon, something like that. And then what I've been doing in this present in the present thesis is, first I was doing all electrode depositions and all. They were not quite promising for me because the activities I have been acquiring with them was like very, very minimal, like less than 1% radix efficiencies. So then what I've done was like I've seen people working with copper nanoparticles, commercial ones, but I felt like doing like optimizing a mechanism for the reduction. So I deployed one grain reducing method, which has ascorbic acid. L-ascorbic acid is the reducing agent, and then here the R is the stabilizing agent or the capping agent that I can call. So here I use PVP. When I don't have any PVP, the most of the copper nanoparticles are either cubes or like cuboids, I can say. They are of very small nanoparticle size and also a big nanoparticle. In general, they are around. I can see they are around 200 nanometer size nanoparticles. And here, when I have a capping agent, which is as I said PVP, the morphology is more changing. It's not cubic anymore. It's a kind of octahedral. And then when I have R15, like when I even further increase the content of PVP, I still have even more amounts of this one is having multifaceted ones. This has both 100 and 200 phases of copper, which is quite good for ethylene production. as stated. So initially, I have done the analysis in the conventional head cell. When I have taken the XID analysis, as I shown, the R0, R15. Sorry, this is missing here. This is R0, R5, and R15. So I have 111 planes on 200 planes in all of them. The ratio is the better. I can say a better ratio in the R15 ones. So what I could see was like there is a higher Faraday efficiency for ethylene at -1.4 with respect to the normal or reversible hydrogen electrode, and then but these are like the activities here for the ethylene. It's the R15 one seems to be quite promising, but it's not up to the mark, like because we have this was done in a conventional head cell. So the results were not so promising. It was like kind of my initial days of getting into the work. And then I have to choose the next step because the small nanoparticles are not so good for my type of electrode reduction. So then we found some articles that are quite promising, like which are published in top journals. Not only the small nanoparticles or very big size of the particles can help, but the optimum range of the nanoparticles can actually help in the reduction mechanism. So what I've done is directly I have taken a copper precursor and then I have carried out the synthesis in a conventional hydrothermal reactor with an autoclave. And then I have got a different, because once I add all the reactants, I don't think there is some way to modify or to control the morphology or how they nucleate inside the reactor. But when I have taken them and then as I've shown you, I have drop casted on them on the conventional gas diffusion electrode and then tested in a flow cell. So when I've seen them in XRD, I have all the types of copper, like metallic copper, copper +1 oxidation state, copper 2 oxidation state, like Cu2O, CuO. Apparently Cu2O, the copper 1 oxidation state is found to be very good for ethylene. And also, of course, copper 1 is good for other products. So when we have seen initially at lower voltages, we have a very high amounts of CO, but then as I was sweeping more towards the negative potentials, towards the cathodic potentials, I have increasing amounts of ethylene, like almost averaging like 30% of ethylene. That's like quite a good amount, or I can say decent amount. So I want in this work, there has been a problem with the current densities. The current densities were not so high because of course we need to have a better energy efficiency. The current densities has to be very high. So more the current densities, the lower potentials, and then which is quite necessary for any mechanism like this. So in the next step, I have used the carbon black, which is Ulcan XC72, and then I just added both of them in one chamber, and then I have carried out the reaction hydrothermally at 160 degrees for like 12 hours, and then I have a platelet-like morphologies. I don't know where they are originated from, but they are like platelet-like morphologies or something. So this is all carbon thing, and then on which like it's nicely surrounded by copper things. So when I have tested this in the flow cell again, so initially I have seen mostly like copper 1 and copper 2 phases of copper here. When I tested in the flow cell, initially at -1.4 or something, I have a decent amounts of CO and ethylene. But when I'm sweeping more negative, like at 1.7 or something, I could see very high amounts of ethylene, like almost like 35%. There are stages I reached almost like 40% of ethylene, which is quite a good number as we expected. It has to be modified even more to reduce the electrode engineering has to be done here to reduce the amounts of hydrogen, because hydrogen it's like unnecessary product or unwanted product that we have in this type of or competitive, as I said, in this type of reactions. So after this, like I thought of seeing, as we don't have in situ facilities at IREC, we thought of seeing some postmortem analysis of the electrodes that we have seen. So all these morphologies have been lost, and we have only like particles that are on this is the carbon torre surface with carbon fibers, and these are the copper, we suppose. So when we have taken the XRD also, what we could see was this is the initial ones which has copper here, and copper oxide and carbon black, that is pre-electrolysis, and this is the post-electrolysis afterwards. So this peak is from graphite, that is from the carbon torre, and then we have seen copper oxide, copper 1 and copper 1. So technically it is not completely reducing the copper oxide to metallic copper because the potential we are applying, it's acting on the electrolyte, on the membrane, on the whole system, but not only on the working electrode or the cathode. So so there is some internal resistance as well. So what we could see even after the electrolysis was some amounts of copper oxide, copper 1, I can say. So we also have done some TM and HRTM analysis thanks to Jody Orbiel from ICN2. So we have got some unexpected results. Actually, we want to see how the nanoparticles looks. We have seen different type of nanoparticles in our samples. Like we have rods, we have cuboids, and we have platelet-like structures. But most of them are found to be around, like the average size we can say around is 500 nanometer size. Which is I don't know, like if we can call them like nanoparticles, because of course they're 500, but they're quite big in size. But the good thing is they're good for our my type of reaction. So these are like platelet-like structures, and then like the platelets we have seen, they are of various faceting. Like they have 200 phases, 0111 phases, and 311 phases as well. And here in this pattern, we can see the idea of having carbon in this particle, in this catalyst material is carbon has to be surrounded by, it has to surround all the copper nanoparticles and then increase the conductivity by better exchanging the electrons in between them. So thereby having more electrons to mediate, and then for the next products, because for ethylene, it requires almost 12 free electrons to participate in the reaction. So from CO to CO2 to CO intermediate, and then to ethylene to form, it almost requires 12 electrons. So the idea is to have a carbon in this, but we have seen like all the red mapping here is cloud-like structures, or maybe we can call them as a graphitic onion ring kind structures that are surrounding the whole copper in the material. So it's quite interesting, but I want to work more on this to have a more controlled morphology, or more like both size and shape modifications has to be done, more controlled ones. And then when we see the productivity rates, of course for hydrogen, the carbon, so what is the advantage of having only copper oxide or carbon black, or only the metallic with the carbon black, and only the copper particles? So here in this, the productivity rate for the carbon black is very high for ethylene, very high for hydrogen, and we have to take care of this by doing some electrode engineering, like by having some hydrophobic effects to minimize the electrolyte passing through it, and to have number of protons, to have a less number of protons available to form hydrogen. And then when we see to the CO, the one with only the copper, it's quite interesting, but it's getting less. But the good thing here is the one for ethylene, the one I prepared with the carbon black is quite found to be quite interesting. Almost like we can see 0.5 micromoles per minute per 1 mg of the catalyst. So this is quite promising, we thought. So I have to modify a bit more, and I think this is going to be published very soon. Like I'm writing already. So to conclude, I can say what I've done these days is I have started with a ligand-mediated green synthesis, which is found to be quite impressive with the morphologies, but the results are not so promising. So then I have chosen to have a Fessel hydrothermal method that can have a different faceted like morphology, faceted like structures for copper. So which is found to be, which can be like I found it to be very good for ethylene and carbon monoxide, of course. And then having additional carbon black to have a better conductivity is having like that's a probe to have advantage to have high current densities. So when I talk in the terms of partial current densities, we are reaching 50 milliamps per centimeter square for ethylene. I think it's not up to the mark like 150, which is published like maybe in a couple of papers, but it's quite a good amount we see. And of course, I'm working to enhance it more to at least like hundreds or 200 milliamps per centimeter square. In terms of low over potentials, also the carbon black, because of high conductivity, high current densities, upon comparing the Faradic efficiency and voltages, the lower potentials, over potentials are low in this carbon black copper composites. So my next steps are like optimizing the catalyst coated gas efficient electrodes. Maybe the composition, like as I've shown in one of the slides, like it has a microporous layer, it has a catalyst layer, and then it has a PTFE layer as a for the hydrophobic effect that can block the electrolyte to pass through. So these are the key targets in the next stages of my work. And then as the title says, modification, like advanced materials and systems. So I have to, for the systems, I have to modify the flow cell setup to have more controlled, more for like controlled mechanism happening inside for a better output. That's the main problem. Main problem I'm going to overcome in the next few days, I hope. And then to conclude, this is my group. So my group is working on different things like redox flow batteries. Mona is working on, and then solar fuels. Victoria is working on. I'm working in electrode fabrication, or maybe energy harvesting, I can say, or of course solar fuels, of course. Power to X, synthetic fuels. He's my professor, John Roman Morante, and my co-supervisor, Dr. Sebastian Murcia, and all these are collaborators. So thanks to DocFarm for giving me this opportunity to pursue my PhD. And of course, thanks to Laura for organizing this wonderful school and giving me a chance to present my work. And yeah, of course.
Thank you.
Yeah. Any questions? Thank you.
Thank you, Tandava, for your nice presentation. Really nice to see the application working, like the material and everything. It's very concise, your work. So if there is any question in the room, let's open first for the seminary room and then for the Zoom.
Yes, we have a question.
Hi, thanks for your nice presentation. It was pretty clear. Just one question in slide 13. It's very clear that on addition of carbon black,
slide?
Yeah, this one.
Oh, okay.
On addition of carbon black, you have observed an advantage, no?
Yes.
Over the, but what can you, this is just a curiosity, what can you tell about the cost effective compared to the copper oxide or other things?
Well, cost effectiveness, I cannot say because all these are commercially acquired materials. So apart from carbon black, I think the cost of it's not like so expensive like graphene. It's kind of cheap. I think we bought like 250 grams for maybe like less than 200 euros maybe. But whereas if you have to purchase 250 grams of graphene, I think it would be like some thousands of euros maybe. So
okay.
I think because this material, the carbon black Vulcan XC72, it's quite extensively used in battery field or in supercapacitors also. So I think it's not that expensive as far as I think. Like graphene, no. Fortunately, I was trying with graphene also, but graphene it is more prone to hydrogen evolution reaction, like which is like a competitive or poisonous reaction for me. So I avoided using that. My initial days, I have tested graphene, of course.
Okay.
Yeah. So cost effective, I don't think it's very expensive material, like, unlike the graphene. Yeah.
Okay. And performance wise as well, it's better than graphene.
Well, it has high surface area, but of course not like graphene. Graphene is having like, it's found to be one of the best materials for sure. But yeah, this is not so expensive and having better conductivity, almost like equivalent to graphene, or having a good surface area as well. Like if you remember yesterday, Anukriti was telling, like she was talking about carbon super P or carbon black, something like that. So all of them almost have like a bit more or less same surface areas, and everything is carbon. Like so, maybe it's better to have other types. I have been like my plan is to test other materials also, but in terms of cost, I don't think they're like as expensive as graphene.
Okay.
Yeah.
Okay, then this is a plus point.
Yeah,
it's not
it could be a plus point. Yeah.
Yeah. Okay. Thank you.
Any other question in the room?
Yes, but one more question.
Hi. I understand that the idea is to have a green system, and using water, of course, is greener. Green, like a green process.
Well, I say green synthesis of nanoparticles only, but I'm not using that anymore because the particles, whatever the nanoparticles I have got, they were not so good as I expected to be. So of course, there are commercial nanoparticles that people are directly testing them in their cells, but when I tested them, apparently, I don't know, they are not working the same. Maybe the reaction conditions are different, or the cell configuration, the flow cell setup I have shown, the configurations are like quite different. This is like a very basic cell that I have been working with, following a very conventional flow of the electrolyte and then flow of the CO2. So, but there are like very advanced things also. So maybe in the advanced side, like having membrane electrode assembly, this having copper nanoparticles, like as I said, green or the commercial ones, they are good. But green for me, like the ones I have synthesized, they're not so good for me. They're not so kind to me, actually.
Okay, well, but my question was like going towards the.
Of course, the whole idea is to have renewable energy sources, or to stop our dependence on the fossil fuels. So, as I said in my first slide. So, sorry. Okay. So here, like having these fuels, like these can be like ethylene, ethanol. They are like quite having very energy efficiency molecules, like carbon organic molecules, I can say. Like we can call them as fuels for sure. And we also have people are looking for methanol economy, as like they want to add it to the already available gasoline or gas oil or something, and then to modify the ratios and then have a better things to reduce the emissions of greenhouse gases, for sure. So the idea is to like most of the ethylene till now is produced by crude oil cracking, and then it's a step, and this ethylene can be used in cement industry, steel industry, and of course the plastic industry, like polyethylene. It comes from ethylene, polyethylene, something like that. So they're mostly dependent on the fossil fuels. See, like crude oil cracking, as I said, like we see in the transport, but we also see the other parts of the industry, right? In the, like, as I said, since the industrial revolution, we are so much dependent on the advancements of technologies. So we use them more and more. So when we deploy this technology of having like reduction of carbon dioxide that we already have, so we are minimizing the effect of greenhouse emissions, and then we can move to a greener or sustainable economy maybe.
Yeah, but I will go to the point then. You're using water in this cell.
Water, no. Catholyte is based water based.
Yeah. My question was, if the hydrogen reduction reaction is a parasitic reaction, have people tried other organic electrolytes instead of water?
People are trying organic electrolytes very early in the beginning, but they are using either mostly water-based electrolytes. So to avoid this, we are coming with people are already come up with the technology of having gas-fed CO2. So what they do is they diffuse CO2 into the electrolyte and they humidify the CO2, and then they pass it to the cell through the catholyte chamber. So having that is like kind of very advanced ones. So my next target is to work on that. Yeah. When you said green, I thought you were asking a question on the green thing. Okay, don't know. Yeah.
Yeah, finish. Any other question? So thank you, Tandava, for your nice talk.
Thank you.
We finish here the last session of Dog Fund Fellows talks. And I leave the word with Laura. Thank you, Laura, for the opportunity to chair today. It was really nice, the experience.
So guys, now we have a little break, but before we go to the break, as you know, let's see if I find it. Where's my, here. Can you see my screen? No, because I'm sharing. Why is not? No, but I am sharing.
Sí, Laura, lo veiem la pantalla.
I think it's in the room that we don't see it. Estic compartint jo,
Yeah, I can see your screen, Laura.
Sí, però és aquí a la sala no la veiem. No sé per què. A veure. Allà on fica zoom de la dreta és la meva pantalla. Yeah. Thank you. So to vote the best talk, you will have to go to menti.com. Okay. I don't know if you know this system, but it's a kind of interactive presentation system. So you have time because we will do the awards after the roundtable. So you can just keep the menti.com, and the code that you will have to enter is 87947263 that you see there. So if you want to take down notes and keep it, I will just leave it there if you want to also. And you can vote there. You should be able to vote. I don't know if it works. It's the first time I use this kind of thing. So, okay, so it's already working. And here I just wanted to put the faces of the people so you remember everyone. I don't know if you need me to remind the names. Ah, yes, sure. So, yeah, the voting is live. So, but come on, guys, just one person each vote, because only one person voted and I see 3 votes. No, I think it's multiple choice. Ah, okay. So, well, as you know, I don't have much idea. Ah, okay, so just choose 3. Thank you, Juan. So you can keep voting. You have all the roundtable session to vote. So you don't have to rush. Do you need me to put the faces? If anyone wants me to put the faces, please say it. And I will say the names. Yeah, don't vote for yourselves as the posters, please. So no, if anyone needs me to remind the names, because I don't want to have like someone be missing because he was the first one to give a talk. So yeah, we will leave this during. Ah, okay. So it says that you can choose as many as you want in order. Please don't add more than 3, so we don't get this crazy. So first, second, and third. But it will be only one award, okay? So let's see if there is no same vote, because I only have one award.
A long week, but I wanted to round up the school with a kind of a different session, not a talk or not so scientific as this school has been. And that's why I invited 4 people that some of them I know personally and some of them I know due to friends and contacts and so on, that they have very different profiles, but that they started like you are now. They did their PhDs. Some of them continued with postdocs and then move on to different careers. And each of them has a different profile. So I think it's very interesting for you to meet people that have followed different careers, so you know how it is done and what you need to do, how you need to focus your career if you want to do these kind of things. So I will start introducing the people we have today. I'm very happy that they joined us. So I will start with Elena Galán. Elena Galán is working at Novalet in Dresden, in Germany. She's a project leader, so she's doing research as you're doing, but in a company. And she's working in organic material development for OLED applications. She studied a chemistry degree at the Universidad de Zaragoza, and then she did her PhD also at Universidad de Zaragoza, where she worked in the design and the study of materials with second-order nonlinear optical properties. And then during her PhD, she performed two secondments. She did one at Georgia Tech in Atlanta, where she synthesized OFET materials. Then she continued in academia, doing a postdoc in Delft in Netherlands during 2 years, where she was developing single molecule semiconductors. And then after this postdoc, she moved to Novalet, where she's working now. So welcome, Elena. Thank you for accepting our invitation.
Thank you very much, Laura, for the invitation and for the organization. I will continue with Lorena Tomás. Lorena Tomás is from a town in Teruel called Andorra, that I didn't know there was an Andorra in Teruel. She manages the research projects and grants development department, working with, as she says, a fabulous team. But well, she studied chemistry also at the Universidad de Zaragoza. This is a coincidence, it was not on purpose. And she was an Erasmus student in the University of Bath. And she says that she loved the city, so she stayed for her PhD. Oh, we have people, okay. Well, she performed bioinorganic chemistry under the supervision of Professor Randolph Cohn. And then she moved to Cambridge to work for the Royal Society of Chemistry. She was a scientific editor for several portfolio of journals. So Lorena, it's very interesting to have her here today because she has different profiles. So she was a scientific editor, and after 8 years of living in UK, she then decided to come back to Spain, and she started as a science communicator at ICMAB, where she is now, before doing what she's doing today, that is the research projects and grants in the grants department. So she has done 3 different kind of works after the PhD. So you can ask her, I'm sure you can ask her a lot of things, because she will help you with your doubts. Then we have Violeta Vázquez. Violeta Vázquez is from Madrid, and she's currently working at Zavala as an R&D and innovation consultant. And she started last year, at the beginning of last year. She's specialized in European projects, more specifically in the advanced material field. And this has an explanation because she did the bachelor degree in chemistry at the Universidad Autónoma de Madrid. And after that, she did a master in molecular and supramolecular chemistry at the University of Strasbourg. And after 2 years in Strasbourg, she came back to Spain to do the PhD, again at Universidad Autónoma de Madrid. And her research was focused on the synthesis of nucleobased derivatives and the study of their self-assembly in solution. And this was done under the supervision of Professor David González Rodríguez. During her PhD, she did a secondment at the Technische Universiteit in Eindhoven in the group of Professor Bert Meijer. After her PhD, she started her training in project management, and after some training and some applications, she finally made it to be a consultant, an R&D consultant in Zavala. Welcome, Violeta. Thank you.
Thank you very much, Laura, for the presentation.
And then we have Julio Ríos. Hola, Julio. He's from Algeciras, and he's working as an innovation manager of INIVICA and the Foundation for the Management of Biomedical Research in Cádiz. Very nice place to work. Which there he covers the activity of all the hospitals and primary care centers across the province. But before that, he has a long career, even though he's very young. He spent his university years in Sevilla and Barcelona, where he developed the interest in nanomedicine. Actually, he was at ICMAB with a high intro. It was a high intro, right, Julio? High intro secondment. And this led him to start his PhD in nanoscience and pharmacy at the University of Manchester. After he secured a highly competitive, I have to say, grant as part of the Northwest Nanoscience Doctoral Training Center that later got the involvement of AstraZeneca, that you all know now. And then Julio, while the PhD and then afterwards, he was specializing in technology transfer, working at 2 world-leading offices. One is the Cambridge Enterprise at the University of Cambridge, and the Manchester Innovation Factory at the University of Manchester. This transition was eased by his knowledge and experience in pharma and biotech, having seen a drug transition from academia to clinical trials thanks to his post at Highlight Therapeutics and Immuno-Oncology clinical stage spin-off from CENIO in Madrid. He was there in Madrid also working. Apart from working as an innovation manager of Inivica, he also works as innovation mentor for Oxentia in Oxford, providing expert mentoring to cohorts from Latin America to help to their projects and contribute to the United Nations SDGs. Thank you, Julio.
Thanks for the nice introduction, Laura. Nice to meet you all.
So, well, I kind of did the summary of your profiles, but I think it's better if you explain yourselves how did you arrive to your current position, if you can tell us how more or less the path that you were following. Some of you have longer transition and some of you it was more straight away, but if you can make a summary, it would be good for them to know. You can start, Julio, if you want, as you were the last to be introduced.
Okay, thank you. So yeah, for me, I think it was initially pretty straightforward. So early on from my degree, I studied biotechnology. I knew that I wanted to do research and I wanted to do a PhD, something, you know, a project of my own, very specialized, and dig in and find out, you know, how could I apply research into something like a drug, for example. So I always had a really translational approach in my head, but it was clear to me that the PhD was the best way of achieving that ambition. Okay. Obviously, thanks to having been in, you know, during my degree in Barcelona, so ICMAB, ICN2, I could explore, you know, research at the highest level. It was really nice. You could also experience spin-offs around. And that felt like something that made me tick. So I wanted to, initially, I already had a thought, like I want to do a PhD, but I also know that I don't want to be a professor in academia. I want to do something, you know, that has an impact. And then when I moved to Manchester, this doctoral training center, which is a really nice thing that they implemented there in the UK, not only trains you to become a nice or excellent scientist, as they say, but also a business person, if you will. So basically, they teach you, you know, how to sell your research and how to identify, you know, the market and ideas that could be developed and how to do that, because obviously we cannot do that completely at the university. And you know, during the PhD, when AstraZeneca came about as well, I could explore further the translation world. And although I did enjoy that, big pharma didn't feel like the place to develop or to have more freedom like you have in academia to think. And for some reason or another, when I saw, you know, back in Madrid, I saw how the drug came about to the market and how science could be done also, you know, from even a place with not so much funding. I developed an interest in helping people achieve that and helping them identify the steps necessary and make the connections, you know, networking to make possible that transition. And that's why I became interested in technology transfer. As Laura said, the UK is quite flexible when you do your PhD. So I already had an experience of technology transfer working for the tech transfer office part-time during the PhD. So it was really nice. You could see how the activities goes by day to day, not only the patents, that's what we normally think about, but also, you know, licensing, contacting industry and so on. And it was totally by chance, you know, when I was working in Madrid and working on this project for the drug, the clinical trials and the strategy to commercialize and improve the patent portfolio, I was contacted by a recruiter to join Cambridge Enterprise, which is a commercialization office of Cambridge. And there I really got the big experience of, you know, of what technology transfer means, especially outside patents. You know, they're trying to become more efficient and also they're exploiting software without patents or the kind of results that you might encounter in your career. And then I suppose because of COVID and because of there being a unique opportunity to come back to southern Spain, in which we don't really have a strong culture of entrepreneurship and even strong science, for example, in my province, in Cadiz, I suppose I just decided to. So that was more coincidental. So it was just, you know, I decided to come back and try and apply all the knowledge that I got there here. And that's me. Yeah, I don't want to, you know, keep going. So yes, please.
Thank you, Julio. I think it's very clear. I think for you it was kind of very spontaneous, like you were changing from one place to another, but not thinking so much, I want to do this, but you were like, I like this, I will try this. So it's very
Exactly.
nice.
It's like not having fear of trying new things, I suppose. Yeah.
Thank you. Lorena, if you want to just make your summary also.
Okay, yes, sure, no problems. Well, thank you for the invitation first, because I didn't have the chance to thank you before. I am Lorena, and I always say that I'm here to stand up for those people who have no idea about what they want to do in their future, because I was one of you. And at the end, it didn't end up being bad at all. I've never known what I wanted to do. The only thing I knew is that I didn't want to do a PhD, and I ended up doing a PhD. So even that didn't work out. And yes, here I am doing a job that I really love with a fantastic team in a place I really like. So don't be afraid, don't be scared of not knowing what you want to do. It's perfectly normal. It will come up. I always say that what you have to do is not to be afraid of making the most of the opportunities that arise for you. And this is more or less what happened to me. I wasn't thinking about doing a PhD when I finished my degree in the University of Zaragoza. And then, as Laura said before, I did an Erasmus year at the University of Bath, and the supervisor of my final year project contacted me to offer me a PhD position. And this is something I didn't want to do. But of course, I couldn't put down such an offer because it was like, come on, Lorena, go for it. So I did, and it was probably one of the best choices I've ever made in my life, because it did change it a lot. I did my PhD there, I enjoyed it a lot, but I knew I didn't want to be involved in academia. Like, I was very honest with myself, something that I think is very important as well. And at the end of my PhD, I realized that I wasn't passionate enough about chemistry to dedicate the rest of my life to it. So I was like, okay, Lorena, you don't really want this. Just jump out from the academic career because you are not interested in it at all, and you are not good enough as well. So I started looking for jobs both in Spain and in the UK, and then I sent an application to a graduate assessment day that was open in the Royal Society of Chemistry, which is the publisher of many chemical journals in the world. And they invited me to the Graduate Assessment Center, and it was a full day of interviews. And when I arrived there, I was the only non-English speaker. And it was a group interview. We were like 15 of us or something like that. And I entered the interview and I realized I was the only non-English speaker. And I said, okay, Lorena, that's it. You have no chances, so just enjoy it. And this is what I did. I enjoyed the interview day. And they ended up offering me the job. So that was amazing. I accepted it. It was a big challenge. It was a job I didn't know what it was about. I didn't know how to perform, but I learned a lot throughout the way. And it was again by chance, because one day my boss told me that he had been invited to ICIQ, the Institute of Chemical Research of Catalonia, where I work now, to give a talk about publishing. And as I was the Spanish there, he asked me to look at the website to check the professors and the research they were doing here. And then when I was checking the website, I saw a job ad. They were looking for a scientific communicator. And it was like, At the time, that was back at 2011, science communication wasn't as popular as it is now, thanks God. That's a very good thing. But back then, there were not many people doing science communication as a career, as a profession. So it was like, okay, Lorena, you are not going to have many more chances like this one. And if you want to go back to Spain, this is a good chance to do it. So I applied. That was, I saw it the day of the deadline, so I had to send my CV and the cover letter and everything straight away. And they called me for the interview and they offered me the job. So I decided to move back to Spain to start working as a science communicator here at ICIQ. Back then, there was not much done, so I had the chance to develop everything from scratch, which was really interesting. But after 3 years or so, I wanted to grow a bit more as a professional and to face more challenges and to have a more managing career. And I decided to look for other jobs. And I was offered one position somewhere else. And then when I said I was leaving ICIQ, they offered me a different position as a manager in a new department that didn't exist back then. That was the research projects department. And of course, I knew nothing about research project management, but it was a huge opportunity and a huge challenge, and I decided to accept it. And here I am today, very happy. I really enjoy my job, and afterwards, if you want, we can talk further about it.
So for you as well, it was not so thought, like you were like...
Not thought at all. My life has been always very chaotic, but you know, it ended up really nicely.
No, because it's different, because in my case, we are in similar positions, but in my case, it was, so just for them to know also, because they don't know me so much. In my case, when I was in my PhD, I already knew I wanted to do project management, research management. So I was looking all the time for positions until I got the one I have today. So, you know, it's for them to know that you can arrive to the same place, just taking different paths.
No, I didn't even know what the research project management was. So imagine.
Yes. Thank you, Lorena. So Violeta, if you want to say it, in the case of Violeta, she has not been in so many positions, but I think her position is very nice as well, because I know that some of you are thinking of going to consultancy jobs. That's why I invited her. So if you can tell us like how it was the change and what did you do to arrive there. So even it doesn't matter if it was like straight away.
Well, first of all, thank you for inviting me here. I also like to say that the initiative I think is quite nice, because we don't really know. Well, personally, I didn't know all the options that I have after finishing my PhD. It was all like pointing out to academia, and even for the people who surround you, like everybody is thinking about doing a postdoc, and you don't have other options to think about. So I think it's really nice to share all this experience with the people that are doing currently their PhD. So well, my experience, my career, when I started my bachelor, I didn't know that I wanted to do a PhD, because I'm quite curious and I wanted to do research. But when I wanted also to go abroad, so I did know that I didn't want to do an Erasmus, because I wanted to focus on my bachelor, and then after that, that's why I applied for a grant, and I have a like ISA grant to go do my master abroad. So I was in Strasbourg for 2 years, and then I get my master, and then I get in touch with supramolecular chemistry. I do love it, and so that's why I came back to Spain to do my PhD in that field. However, when I finished my PhD, I did look for options to carry out my research in academia, but I did not found at the time something that fills me, because there were not so many options in Madrid that I couldn't move, because I had already started a family, so I couldn't go then abroad. So I started to look for another options and other careers that could be also creative, and that could be also. I do not like to work in a job that every day is the same, you know. So I started to look on other options, and I found out that the consultancy could be one option, one interesting option. I started to do a course in project management to familiarize, because for me, I didn't know how that worked. The only European programs that I have known was the Marie Curie or the ERC grants, but I did not know that there were big projects involving consortia with also research institutions that carried out low TRL projects with a kind of breakthrough advance, but they were also collaborating at the same time with companies and really going through the market. And so that was new for me. So it was good for me to do some kind of formation before this transition. But I really found out that there is quite an interesting job to do this, because you work with different clients. So every time the field will be a little bit different. So you are not so focused on the same field every time as I was in my PhD, because when you specialize in such a small area, then there are a lot of things that you are missing out. And for me, this is quite new and interesting, because I learn every day about different things. We need to be updated at all the roadmaps and all the things that at the European level are carrying out by other research groups. So I think we are still in touch with research from another point of view, and I think is quite nice. And I still have to think every day, so there is not a mechanical work. So I don't know. I'm quite happy with this new look for the research, but yeah, I do sometimes miss my laboratory work, because that's true that it changed a lot to be every day with the laptop instead of with your lab coat and doing experiments. But I do think that is also a good job for a PhD, because at the end, I think everybody shares that we are curious and we want to learn something different. And I don't know. So as Lorena has said, don't be afraid. There are a lot of options after. So if you are not interested in going to academia, you will find a lot of different options to carry out after your PhD.
Thank you, Violeta. Very nice.
Thank you.
I think in your case, it's very nice to show that your limitations, like you didn't want to leave Madrid, are not a problem if you are creative and you are curious. Like if you train yourself and you are curious to know what you want to do, I mean, now with internet, you can know everything. So if you're curious, you will be able to find something, and you can learn yourself a lot of things. So don't think that your limits are a problem for you. So you can always change the perspective. So very nice, Violeta. So now, Elena, if you want to also explain a little bit.
Yeah, I will do it a little bit. So after my bachelor, it was clear for me that I did want to do the PhD. I was a bit doubting, because I joined the first ICIQ summer school in 2008, and was really nice. And therefore I was a bit doubting. Do I go back to Zaragoza? Do I stay here in Tarragona? At the end, I went back to Zaragoza and I did my PhD there. And I think what I was missing a little bit was applied research. So after my PhD, I wanted to stay in Spain, and I was looking for some jobs outside academia. Back then it was hard. It was actually impossible for me to find anything. So I decided to do, to bridge the gap a little bit with a postdoc in the Netherlands. That was a very nice experience. I spent 2 years in Delft, beautiful city, very nice people. I really enjoyed it a lot. But again, this career was not what I was really looking for doing many years later on. So I started to look for some other jobs. Again, I wanted to go back to Spain. I did some interview in a patent firma. Was quite successful. They invited me for a week to join the company and see what they do, how they work. And I realized it was a bit too monotone for me. It was not really what I was expecting. So I went back. I continued my postdoc for a couple more months, and I had to prepare actually some review about organic semiconductors. And while looking on the internet for some information, I came up with Novalet, and they had an offer, a job, a vacancy with basically my background written in there. I was like, okay. It's not in my plan to go abroad again. I don't speak a word of German, and this is Eastern Germany. But yeah, let's give it a try. Why not? So I sent the CV. They called me after, I think I did 3 interviews. Then I got selected. So I moved there. I have to say the first 6-8 months were really difficult. First of all, because it was my first position out of university. Second, in Germany, without knowing anything about the language. And also, the people are a bit more reserved to what I was used to in the beginning. So it was quite of a shock. With the time I was getting used to that. I learned German, and also in the company, I was so evolving a little bit. I started taking care of some technicians, being responsible basically on the synthesis. And then I moved to more customer-oriented targets and project leading and so on.
Thank you, Elena. And there in the company, are you still focused on research, or are you more like leading the team? And so, like, if you can tell us a little bit about your work there?
Yes, so purely research. So from idea generation to synthesis of molecules, purification of molecules, then combining with engineers and physicists, we build up the OLEDs, we test the molecules, we evaluate the results, and then all the IP protection and customer introduction.
Okay. And for you, what's the main difference to do research in academia or in a company?
You see much more dimensions in the company, and this link with the customer makes everything a bit more goal-oriented. You know what you have to do, and you know why you have to do, and you see the end. Let's see.
Sorry for that. Someone came in the office. So thank you all for this nice explanations about your paths. Now I open for questions for the PhD researchers. I would just take the advantage of having these amazing people here and ask all the doubts that I would have had, that I had in my time. So there are people in a room that have a microphone, they can ask anytime, and people in the Zoom, you can raise your hand. So I leave 30 seconds to think a question. If not, I will ask questions. Right? Oh, if we have Mona Lisa. Mona Lisa, you can ask.
Yeah. Hello, are you getting me?
Yeah.
Okay. First of all, thank you all of you for your nice giving us the details that what you have done and what you are doing now. It's really nice to know, as I'm the PhD finishing almost in a couple of months. So now I can think a bit what I'd like to do after the PhD, not only the postdoc, or maybe I have some other options to do just when I came to know from you. So I have a question to Elena. So hi, Elena. Yeah, so as you are doing research in a company, so could you tell me like how open they are, like as a scientist you are, as a researcher, they are you like are you the master of your own, like can you do it very independently, or you still have some you don't have the complete independence to do the research what you want to do?
No, I guess in the company we are very limited, let's put it this way, to customer requests. If it fulfill customer requests, then we have a lot of freedom, let's put it this way. We are really a research company, and let's say crazy ideas are always welcome, and we are open to try new things as far as it fulfill some customer request.
Okay, thank you.
Welcome.
Question here.
Regarding also research in companies.
Say your name, please.
I'm Juan Carlos. Regarding research in companies, how do you there is no centralized way to look at this. So how do you find a way to a place like this? And how do you research jobs and stuff like that?
Are you asking to Elena or to all?
Elena mainly. But
in my case, it was in my case it was just by chance, basically. In this case, I was looking for information to prepare some presentation about organic electronics, and I came up with Novalet. I didn't even know that the company existed before, and therefore, they had a vacancy, and I just sent my CV.
I think.
Yeah, sorry, Laura, go. I was going to add in. So.
Yes, I know. I just to add, like what I said, I think it's a matter of being curious and just checking everything and lost yourself in the internet and read a lot and ask people. Also, I am always asking people, what are you doing, and try to know people, and it's like contacts work a lot also. So
yeah, I think contact is also the best way to learn and to decide yourself what would be the next step.
And also don't think too much. Like if there is an opportunity, just go. You can always change. Like you're young, you're starting your career, so if you spend 1 year in a place you don't like, then you can change. There is no problem. And Julio, if you want to say something.
Yeah. Definitely agree with what Elena and Laura said. So basically, you can always send your CV and have a look on the internet. That definitely helps. Now, I think most of you are in Barcelona. That's probably one of the best cities in Spain to have events, networking events where people interact together, you know, academia, industry. Just go there, speak to people. You'd be surprised, especially in this country, you know, networking does a lot. So you need to know what they're looking for, or you need to approach the person and ask them a witty question maybe, and, you know, find out what they're looking for and what your background, how your background can benefit the company, basically. Obviously, having also a more commercial approach helps, not talking only about publishing papers. Normally they are a business, so they need to survive and they need to do something innovative. And again, you are in probably the best ecosystem here in this country to do that. So benefit from that. And LinkedIn as well. Lots of LinkedIn for Spanish speakers. But yeah.
More questions? Come on, don't be shy. You have been asking a lot. Fabiao. Fabiao?
Yes, hello. I was misclicking a lot of times. I don't know if I'm nervous or what. I was just misclicking a lot of times the microphone. Anyway, my question is quite general, and it's open to all of you. I really will be glad to hear your opinion about this one, because sometimes it's not only academia or industry. Sometimes we also heard about being a freelancer. So if a scientist after a PhD, which have a lot of soft skills, I don't like very much this word of soft, but anyway, it's what we call them. I think we as scientists, we have a lot of soft skills that are paramount to the success as a freelancer. What do you think would be the areas that companies are looking for more from the point of view of a scientific background to contract as a freelancer? I heard a lot about editor, writer, science communication, also consulting. But from your point of view, do you think there is a more broad spectra?
I will say thank you for the question. I think you have mentioned the most important fields in which you can work as a freelancer, as a scientist. I don't know if there are quite some more, but I will say that before going to a freelancer, for me, in my case, it has been quite nice to work in a company, because even though I have the soft skills you have mentioned, for example, we have scientific writing, analytical thinking. We have also a lot of the scientific methods help us when you commit an error to go back and then to start from the beginning, and that there are some things that people who has not done a PhD doesn't know how to work with it. So our mind, I think, is set to do a lot of different things, and sometimes the companies they don't know really our potential. But however, I will say that to be more familiar with this task, I will go with a team before going as a freelancer. Even though we have the capacities to do it, I think it's from my point of view, it is better to have a formation with a team, and then maybe you can go as a freelancer. But I will say that I will not have learned to write proposals, for example, or I will not been able to review them without being working with my European team in Zavala. That's my vision.
Any of you want to add something else? I don't know. Lorena, that you were an editor and so on, so maybe you can add something.
Yes, no problem. I totally agree with Violeta. I'm fully aligned with what she has said. It is true that when you finish your PhD, you have a lot of knowledge and you have many skills. Let's not call them soft skills if you want, but you don't have the experience of working in another environment outside academia. And it is true that this is quite different from being involved in a PhD, working at university. It's a completely different world. It's not too challenging, but I think it's worth experiencing it because you do learn a lot of things from working in a company, working in a team, having to fulfill different objectives, because when you work outside academia, you don't care that much anymore about scientific objectives, but other sort of indicators and managerial objectives. You have to learn to work in a slightly different way. And if you jump into freelancing, which is a very attractive world, but it's also very risky. I don't know if the risky part of it makes it attractive as well, but it is a risky thing to do, especially without having experience. And I think I agree with Violeta. I think freelancing can be interesting, but you need an even higher set of skills because you have to manage yourself. You have nobody to teach you anything. And that is really, really challenging. So when jumping into the freelancing world, you have to be really, really sure that you can do it by yourself. And that is not easy at all. Like I wouldn't have been able, for example, I started working as an editor for journals. I wouldn't have been able to do it on my own. Even though I had just finished a PhD, I had a lot of knowledge on chemistry, that is what I needed, but I knew nothing about the rest of it. And it's a really wide world. It's the same thing I was working in science communication, and I thought I knew how to write a press release. But that was my thought. That was quite different from reality. I had to learn how to write a press release. I had the competencies, I had the knowledge, I had my writing skills, I had my communication skills, everything. But I didn't have the view of what the rest of the world expected from me, you know? So I think it's good to start working first in a company, in a team, get some experience, learn more, and then if you think freelancing is the way to go for you, then you can jump into it. But before, it's a bit too risky from my point of view.
Thank you,
Yeah,
Lorena.
definitely. I definitely agree with that, actually. That was perfect. I think the first question for me would be risk. Like, honestly, frankly speaking, from a personal perspective, are you willing to assume that risk? Especially what Lorena said, like you're out of your PhD. Unless you have a really nice network that, you know, you could find potential clients of something that you're offering. For example, academic consultancy. I've seen that quite a lot of people out of the PhD doing that, or during the PhD doing that, and they set up their own business, right? If you have a network of people you've been working with and they're willing to pay for your services, and that's a way of starting, okay. But then if you've never worked as part of a team, you don't know industry, you don't know, it's a bit tricky. I think it might be risky, it might be an experience, but again, it depends on your personal situation, I would say a lot. Also in the country you set up the business, okay? In my opinion, this one is one of the worst in Europe because of the way that the whole system works. For example, in the UK, when Laura said I was working as a mentor for Oxford, that was released in the UK. You can do it on the side. I have my own sort of, it's not a business, but you know, my own consultancy services on the side of my job. And that was really easy. You declare taxes and that's it. Here, it's a bit more tricky. You're not able to invoice. So, you know, think about all those questions as well, because it might be bureaucracy heavy. And I don't know if you want that, especially at that early stage, okay? Talk to people who set up businesses and see what they can tell you. That would be my advice.
Thank you so much. I'm very happy I could hear from different, well, your different opinions that somehow are quite common between you, but hearing from different people, it's good. So thank you very much for sharing.
Thank you, Fabiao. And also, as Julio says, everything is networking. So I will send you the emails of the four of them. So if you anytime want to ask them something, you can always contact them and share experiences. So they will help you for sure. So we now have Carolina, who has a question.
Yeah, hi. So thank you, everyone. It was very nice to hear all your experiences. I think I have a very short question, maybe to Julio. Well, it was very nice to see how the process that you liked research, and then you also took courses in management. And then after all your experience, you decided to go back to your region, to Cádiz, if I'm not wrong. And I just wanted to ask, did it feel, after all your experience, after all you've done, did it feel like a leap of faith to go back to a place that, as you said, didn't have so much development on your field, or didn't have so much, let's say, so many companies and things like this? For example, in my case, I always think like, okay, I want to do my career, expand my profession, everything, and then go back to my region, to my place. But then I think, okay, there's not so much. So does it feel like a leap of faith to just say, okay, I'm going back? That's it.
I think we lost Julio. Julio, we cannot hear you.
Yeah, problem with my connection. Yeah, on time.
Yeah, just on time. But were you able to listen to the question, or?
I think I was left at faith. Do you have any faith? And then
the last part was like the leap of faith to just go back to a place to where you want to go back, but that you know that there's not so much, let's say, opportunity as it is where you are developing your career.
Sure. Yeah, I do get the question. So thanks. That's an interesting question. So again, it depends for me, and always really clear. It depends what you want in life out of your career, okay? If my career was everything to me, probably I should have stayed where I was, because you can learn so much more. You are exposed to, you are in a unique place worldwide. Now, however, do I feel personally better with the job that I did there or that I'm trying to do here? I think what I'm trying to do here, and as you said before, I've identified my region is not strong at all in healthcare innovation. Researchers don't have an entrepreneurship culture. They just basically focusing on publishing papers, which is fine, because most of them are clinicians. Their main goal is to take care of people and take care of their health and everything. And they have many challenges, especially nowadays. But when I was for example, in Cambridge, yes, you deal with many agreements, you interact with the main companies in the world, but I felt like, yes, I was producing, for example, success stories and money for the researchers in the university. But at the end of the day, I was part of an office of 80 people, and everything was well established. And, it becomes, for me, it wasn't, at some point, it's not challenging anymore, or it's not as rewarding. Here, if I meet a group of 20 researchers and then suddenly they learn what a patent is, or how to commercialize software, or how to implement a solution to help people diagnose a disease earlier and save costs for the system, I feel better. And I feel if I connect them now, I'm trying to make connections, with the Catalan ecosystem, with Madrid, with trying to let them see what success stories they can have in our own country. I think that's more rewarding for me. So I think rewarding was, yes, I have faith. I have faith still. And it's really beautiful when you work towards something that is, connected to your own being. So yeah, I think it's a combination of factors. That's for me. So yeah, I think it's a great thing to implement everything. Of course, legislation and the culture is different. So you cannot copy paste. That's impossible. But you can adapt. And I think, yeah, I definitely encourage you all, if you reach a point where you're saying, okay, I can improve much better in this place, but I can offer to people something else there, back home. I think that's nice to do. And you can always go back if you want to, or go out if you want to,
Okay, thank you very much. Very nice to know.
Thank you. If someone wants to add something else, I don't know if the girls want to say something. If not, we have another question, but if you want to... No, I think Julio was pretty clear, so. So we have a question from Johannes Groen.
Yes, thank you very much. So my question is like a bit different topic. I was wondering about specialization. So I have been on.
Sorry, Jan. Are you asking to all of them or
to all of them? Yes, yeah. Just in general. So on different conferences, I've heard different like advices. Let's say some say you should specialize into one field and like stick with it and become an expert there. And others were like, well, if you know more fields, you can maybe do more collaborations, do more research, you know more. So I wanted to just know if you have any experience or advice also with regard to in the industry, what is more valued there compared to research, let's say.
I think it's yeah. Okay, yeah. Thank you very much for the question. I think it's very much dependent on each person and personality. I mean, if you are, for example, a very open person and you are, and it's very easy for you to communicate with many people, maybe you can learn very easily from different persons and be a bit broader in your experience. It can be that you, for example, like to work alone and, you know, work on your own project, and therefore you are an expert on whatever you are doing. And from my point of view, it doesn't really matter. Either way are good. You have to just know a little bit what is better for you. You have to know, I think the key is to know yourself and to follow your instinct a little bit.
I'd like to add something. It's completely aligned with what Elena said. But for me, the most important thing is to be good at what you do, regardless of what you do. You know, if you are really good at something very specific, then it's perfectly fine. If you are really good at many things at the same time, it's perfectly fine. And as Elena said, it depends very much on your personality. I think one important thing is analyze yourself, like know yourself first and know what you enjoy doing, because normally what you enjoy doing is what you are good at. Because normally you enjoy doing those things because you are good at them and it feels really good. It's very rewarding to be good at something. So it doesn't really matter if it's very specific or if you are good at many things. It's perfectly fine. I always say I've never been good at anything, but I'm okay-ish at many different things. And it has worked out perfectly well. The world is evolving towards multidisciplinarity, interdisciplinarity, and all of those things. I think the most important thing is be good at what you do, full stop.
Good point, Lorena. I think also I would add something. I think it depends also if you know what you want to do. If you have a very clear idea, I want to do this, I want to work on that, I have this project, I believe in that, like you have to specialize in it because you want to do this. But if you are adapting, it's better to have a broad image of not everything, but at least some different aspects, because if not, if you don't know what to do, but what you're doing, you're specializing, you're not sure you want to continue with that, like you can continue with it, but at the same time, you have to try to know other things as well. So I think it's also important, this.
But it's also like the saying, no, like a jack of all trades, but master of none. Like if I like just try to find a lot of different things, will that not like hinder me finding a nice postdoc or a nice job?
That's why I say not everything, but at least, like for example, in my case, I did a postdoc, but while I was in the postdoc, as I was not sure I wanted to continue, I was already training myself with project management. So it's like you don't have to know everything. I don't know anything about being a communicator or being an editor. But while I was doing one thing, I was like, okay, I want to check also this other thing, and I'm going to I mean, of course, you have to spend a lot of time and you work long hours because aside from your job, you have to spend a lot of time training yourself. But then it's worth it. But this, I'm saying, if you are not sure of what you are currently doing, but if you really like and you want to continue this path, just focus on being the best on this. That's what my perspective. Thank you, Johannes. I don't know if you want to ask another thing or that's it.
No, that was it. Thanks.
Any other questions? I don't know if in the room there are questions because I don't see it. I see a hand.
Hey, hello, it's me again. This time I found my mic faster, so I'm getting better on this. The question is, I think, of course, the mindset is paramount to the success, and having objectives, it's of huge importance to keep motivated, because when things are not going well, we have this goal, we know where to go. However, I have to say that by speaking with my colleagues, a lot of us, we still don't know very well. Okay, we know we have this ocean of opportunities, but we still don't know very well where to go. However, I think, and I would like to know from your opinion to all of you, if you pass through this process or not. And if you agree that a good process would be, because for example, Lorena was commenting that what am I good at and what do I like to do? Because sometimes these two merge. But further than that, what does the world needs? What does the society needs? And then will a client pay me for this? I think when we have these four together, what am I good at? Do I like to do it? Does the society needs this? And will somebody pay for my service or product? I think then if we have something in common in these four areas, it could be a good starting point. I don't know if any of you passed through this, or maybe there is no need to go through this. I don't know. What is your opinion?
Thank you. I think it depends also of your personal situation or what do you want in life. I mean, as Julio mentioned before, if your career is the main focus in your life, then you may not, you can move, I don't know, to another country or region and you don't mind, or maybe there is something limiting to you, like you want to stay. So first I will focus on my personal situation and what do I want in my life. Like is my career my first option, of is I want to stay here, I don't know. And then I will search for the options I have and matching with the things that I like. I mean, I do really like research, but at the time it wasn't a real option for me, because staying in Madrid, there were not a lot of opportunities. And if I really wanted to become a good researcher, I do have to go abroad. And that wasn't an option for me because I didn't want to move, and because it wasn't just myself, but also my couple, my daughter. So it was like kind of tricky. I will say that the first thing is your personal situation and what do you want in life. Because I think even if the research has a lot of good things, it's also really, really a sacrifice at this time. Like you maybe need to put a lot of hours, and maybe you can't, or I don't know. It is different situations in the different countries. I think it works different, and I will say that yeah, I will match my personal situation with the things that I like. It's like when we talked before about the risk. If you want to become a freelance, maybe it is not possible in Spain, but if you are willing to go abroad, maybe there is an option for you. So I think it's kind of tricky to match all these things together. And the more difficult for me was to know about what are the other options. because when you are in doing your PhD, I only knew about the academia. I did not know the other options you can have and where I could be useful, as you said. And I think little by little, the people who have been trained with a PhD are becoming more, well, the companies know what we can offer, all the skills we have. And I think it will be little by little easier to get different positions and to be considered like professionals as we have with such a range of different qualities and capabilities. I don't know if I really answer your question, but yeah, I will say that it's a tricky question. I don't know, to match all these things together. No, it's not easy.
But thank you. Actually, I didn't expect the exact answer. Yes, you need to do this, this, and this, and you are successful. But it's always good to hear the point of view from your side. So thank you.
We have a question on the room, Laura.
Yes, Artur.
Exactly. Yeah. Hi. Thanks for your nice introductions of yourself. I think all of you have a very interesting career path so far, and I actually want to pick up a certain aspect of what Fabiao asked previously. It is about taking risks. You mentioned, for example, that right after the PhD, maybe it's not the best point in time to become a freelancer because we lack still some experience in fields like the industry, the applied field. But do you have some risks that you thought they were definitely worth taking in your career path? For example, I'm thinking of Elena. You went to Germany and you said the first few months were very complicated for you because the people were also a bit reserved because of the different culture. But do you think this risk was worth taking? Have you been rewarded for it? What did you take out of it? And yeah, it's also an open question to the entire panel.
Thank you for the question. In my case, it was definitely rewarding. And I think in general, you have to take risks if you want to grow and if you want to learn. There is no better way. I mean, if you are always in your comfort zone, yeah, I mean, you can have a happy life, can get a bit boring or monotone at the end. So I would really, motivate the people to take risks. And as we commented already a couple of times, you can always leave and start something different if for whatever reason doesn't work. So there is always a way back or a way to somewhere else.
Yes, I think Lorena, yes.
I can also comment on this because it's a really good question, and taking risks is not easy sometimes. And I think everyone takes risks when making a decision. Every time you make a decision, you are accepting the risk that comes as a consequence, right? And I like when you ask, was it worth it? I think you have to make it worth it. I mean, you are responsible of what you make out of it. You accept the risk, it's fine, and then you have to make it work. And even if it doesn't work, it will be worth it because you will learn along the way, and it will help you find what you want to do. Even if that didn't work, you know that this is not what you wanted to do. I think, especially when finishing your PhD, that you are normally young and dynamic, and you have many years ahead of you. It's the right time for taking risks if your personal life allows it, of course, because it's the way of progressing and learning. And for me, in my personal case, I did take a risk when I came back to Spain, because I had been living in the UK for many years, and I had a permanent contract there, a lot that I really, really enjoy doing, loads of friends. So my life was there. And suddenly this opportunity came up that I wasn't even looking for, and it shook my head, you know. It's like, well, maybe I should give it a go, because I've been here for so long that I should give it a go. And I accepted a job in a place I didn't know. I had no friends, no family whatsoever here. I was offering a lower salary, and I gave up a permanent job for a 1-year contract. But it was worth it, absolutely. And I think I made it worth it as well, you know, because I worked really hard for it, and I'm really happy. So don't be afraid of taking risks, even more at this stage of your career.
Thank you, Lorena. Anyone else wants to add something? No? If not, we continue with questions, because we have more questions. There was Mona Lisa, but as Mona Lisa already asked one question, if you don't mind, Mona Lisa, we pass to Nikki, and then you, Mona Lisa, okay?
Okay.
So Nikki, if you want to speak. You are muted, so Nikki. So maybe Mona Lisa can ask, and then Nikki.
Hi.
No, so we have Nikki already. Yes, I can hear you, yeah.
Now, can you hear me?
Yeah.
Now can you hear me?
Yes.
Okay. Okay, good. I have a question. A while ago, I think it was Lorena that said that in choosing your what you want in the future, it should be like an interplay between how good you are in your job is how you want your job. I mean, how it relates to how do you want really the job, you know, or if you are excited in the job. So I mean, before I have my PhD, I am in this position finding jobs. So I was in academe for a year teaching, and I know that I know at myself that I want to have this job, because like in choosing job, you need to have like stability, like you have a stable environment, stable job, and most importantly, researchers, we love the challenge and excitement, you know, like the fire that we want to continue the job. So at some point I get like bored, like this continues, like the same over and over again, like teach and then the same stuff, doing stuff. So at some point, for sure, in the future, if I'm going to do again a job, it will be like at some point you get stagnant, you get like bored. So my question is how to get back this fire, the thrill, the excitement in getting this, you know, getting this continued job, and like how to motivate yourself. And it's like a general, any of you, if you have any comments for this. Did you get it?
It's a bit tricky to answer this because also I think it really depends on, I'm research, but it really depends on the job. For example, what I do now, working for technology transfer, you do so many things, so many different things that you don't get bored, and you can always motivate yourself in a different aspect. So you have to communicate with companies, you have to communicate with researchers, you have to communicate with the patent people, you have to, so you know, you attend conferences as well, or you actually help them write a scientific project. So you do so many things that it's really difficult to get bored, and you motivate yourself, or someone motivates you because you work with a lot of people, or a project motivates you. Now, but otherwise, what I suggest, what I've always done, is to be involved in different things outside my job, like, and then see what someone else is doing. I think that's the most important thing for me. And then perhaps I'm rethinking what I want to do, or perhaps I'm rethinking the way I do things. and reshuffle my thoughts and maybe go for something else, or stay where I am, appreciating the good and the bad things. I'm sorry, but I think most of the jobs will become monotonous at some point. It's just the way it is. But yeah, it's tricky. Perhaps just try to do different things outside the main, the main job, and keep exploring. Keep yourself open-minded, like in a PhD. Keep yourself open-minded. I was doing biotech, then suddenly I went to Barcelona to do synthesis of materials, and then suddenly I transitioned to something else. So I don't know. It's just it's tricky. I don't know if anyone else can help me here. It's tricky.
Thank you.
I agree that you must. It's tricky, and I don't know how to answer. But in my case, it's not a monotonous job because we are writing projects, and each time is a different project in different with a different aim, with different consortia. So any time is different. We also manage European projects, so there is not always the same. So, and you are always learning about different fields and also different situations where we are also very updated of what is at the European level, or the research line, the main research line that the European Commission wants to bust in order to lead the research at the European level. And I will say also that networking and always being open is always a good option. But I don't know if in 8 years or 10 I will be in my current position. I mean, I am being always curious, and maybe in some years I found something that fulfills me more, and I will then change. I mean, I will say that keep your mind, as Julio said, open, and yeah, there is something that you can learn in a new position, and maybe you know someone and you can learn about the different options, or I don't know. But being open, I think, is the main thing. And you will, I don't know. I don't know if I will be writing proposals in a few years, or maybe I will learn something new, and then I will say, okay, I want to work on this. I will keep my mind always open.
And would, for example, company size be a key factor for you, in the sense that, I mean, I can imagine in a small company, if you start doing some work, you will always be doing that same work. Whereas if you work in a bigger company, multinational company, something like that, I mean, you can start, for example, in R&D, then move to, let's say, upscaling or product development, then move towards customer, then sales. You have many possibilities. So that might be something more suitable for you.
Yeah, but like, say, for example, at some point, it will take years for you to move up, you know, and then you will get somehow.
But you are not in a rush.
But I mean, if you will get in that point, just ask you.
Don't think that you want to be in the top in the first year. Like, things go little by little, go with the flow.
Vale.
And don't be too demanding either, because, you know, I love my job. I do love it, but sometimes I get bored as well. Like, everything has ups and downs. And don't give up on something just because you have a low time, you know. Maybe you have to give it another go, and then, you know, if you decide that you don't like it, then change. But don't be too demanding. Things takes time. It's very difficult. No one knows, when you start doing a job, no one knows the day-to-day of that position. Maybe you thought that you were gonna love it, and then you realize that it's not what you expected, and the other way around. So just give it a go, be patient because things takes time. And at the end, if you decide that this is not what you expected or what you wanted to do, then change. But give it a go first.
Thank you to all of you.
Thank you. That's a good. That is a good. Thank you.
We have a question from Mona Lisa.
Yeah. Hello. Again to Elena. I would like to ask you, like, when you first joined from the academics to the industry, so how was the approach from your fellows, like your group, your other colleagues, like in terms of when you are joining for the first time? Definitely, anybody has to learn a lot of things. So as per the how the work is going, what my job. So in that learning the learning time, how much you got the help from your colleagues and definitely also from your boss? For example, when somebody is, for example, I'm doing PhD, definitely I'm getting help from my supervisors. Besides, I'm getting help from my group members. The help regarding the science, the research, and also some philosophical training also, like kind of the motivation. So maybe I'm not asking about the motivation or the philosophical, but from that regarding to learn the work or the job, how much help you received from them, from your colleagues?
Mm-hmm. I think in the company you always receive a lot of help from everyone, not only from your direct boss, but from many different people in many different departments. In a company, everything has to be done in a certain way. And there are, for example, work instructions for almost everything. So if you want to do a reaction in the lab, you really have to know what you are allowed to do and what you are not allowed to do. So in this sense, you do get all the information you need. And if not, you know who you have to ask. In my particular case, what I struggled, as I said, was with the language. From the beginning, I was supposed to supervise 2 technicians. They were not the youngest in the company, and they were not able to speak a word of English. So that was really hard. And yeah, I mean, we had to communicate basically with hands or just ask someone for help for us to communicate. But apart from that, everything will be clear and there will be someone that will explain you what you have to do, or you have the work instruction to go through. So that shouldn't be a problem at all. You will always have enough support.
And okay, that's great. And also their approach is very professional, no? Because their approach is very professional, no? Like, because they are it's a company. So like that.
I didn't understand your question.
Are they very professional, no? Like professional.
Yeah, they are definitely. Yeah. Okay. Therefore, I mean, everything has to be done like to the letter. Therefore, everything is written, and you have like a procedure how to move on in most of the cases. So everything is very controlled there.
Okay. Okay. Thank you.
Welcome.
More questions?
We have another question here in the room. Go ahead.
Hello, thank you for sharing your experience with us. I am Raphaelle, and I had a question on a more personal aspect, so feel free to dodge if you don't feel like answering it. I'm more a person like Violeta. I want to settle down after my PhD, but I wanted to ask for the other person who have traveled after, how do you manage your family life? Do you bring your companion, girlfriend, boyfriend with you when you travel, when you change from city or even country? How hard is it to mix the professional life and the personal life in that case?
I think Julio can start, no? Maybe?
Yeah, I mean, for example, earlier on in my career, perhaps I didn't have any sort of anyone with me or any responsibilities. It was easier to move around. Then for example, when I came back to Madrid to work for a company and then the offer came about for Cambridge, I don't know, talk to your partner, say what the benefits may be of moving or not, because obviously you have to think about the job of someone else, not only yours. Obviously the UK is a place where you could pre-Brexit find a job without any visas or any requirements. That's easier, of course, that helps. Then if you and your partner reach an agreement, if you have family, I don't have children, so that's easier. I do have dogs and cats, so I had to take them around and arrange for a lot of paperwork. But I think it depends. If you really want to do that and try, again, I was thinking of going to Cambridge, you know, one of the best offices, blah, blah, I'm going to stay there forever because I have a permanent contract and, you know, I'm going to progress to senior and manager and so on. So I was thinking, let's move for 5, 6 years and then, you know, we'll think it. And then suddenly it was 2 years and we're back. So if you really like the position and your partner is able to find another job or make a life there, or maybe even sacrifice his or her career for you for a couple of years, and I have some friends who've done that to take care of, you know, I have a friend, she's a researcher, she went to do a postdoc in the UK. Her husband decided to take care of her children, which is, you know, it's okay as well. And he decided to take a time off. So, you know, I think communication is key here. And don't feel bad if you say, oh, maybe I'm not going to like it. I feel bad because I'm making my partner move. You know, at the end of the day, it's a decision of two. And if you're really happy and decisive about something, just try it.
Thank you, Julio. Anyone else wants to add something? Well, we have the opposite side of Violeta that didn't want to move because she had a family, for example. And this is something very personal, and each one has to arrange their things. I mean, sometimes you can do it, sometimes not, and both options are okay. I mean, it's always, as I said, like 3 times already, go with the flow. There are more questions in the room, or no? So then maybe
No more questions, no.
No? So from my side, I had prepared a lot of questions, but as we are finishing the time and I don't want to take people's time, I am so thankful that you wanted to join us this roundtable. I mean, I wish I have had this opportunity in my PhD. So thank you very much for your time. I'm saying all of this so in case anyone still is thinking for a question, no? So then we will finish here. Thank you to all of you, the 4 of you, and see you around. I hope I will meet the girls I haven't seen in person soon, and the others I hope to see you too. So people, we are finishing our summer school. We will continue now with the awards of the best talk and best poster. I will go to the seminar room of ICMAB. So we will take a minute because I have to move there now. So if people that are at ICMAB want to go there to the seminar room, so we are all there to meet the awards. I have a lot of noises. I am muting all of you. Yeah. So if people are at ICMAB, can you please go to the seminar room and we'll meet you there in a minute, okay? Thanks to all of you.
Thank you and good luck, everyone.
Thank you.
Thank you and good luck. Stay in touch if you want.
Yeah.
Yeah, I will send you the emails of the 4 of them so you can contact them and just if you have more like personal things to tell them so you can chat with them. Thanks.
Thank you. Take care.